Pleased to announce that the Grabchenko 6 International Conference, Advanced Manufacturing Processes, is starting despite the big problems in our country. This conference, like the previous two, is taking place in the context of a full-scale war in Ukraine. Yes, the war in Ukraine has been going on for 31 months, and last year there was a missile attack on the Odessa Polytechnic. This did not break us. You see how quickly our buildings are being repaired. We are sure that our university will become even more beautiful. The current situation does not allow us to hold the conference in the usual mode. Most of the reports will be presented online, and some reports will be presented here in the conference hall of the Odessa Polytechnic. We expect conference participants from Zaporizhia, Kyiv, Lviv, Ivano-Frankivsk, here in Odessa. We hope that the number of participants coming to Odessa will increase. And now, I invite to speak the Vice Rector of the Odessa Polytechnic for scientist work, Professor Dmitry Vladimirovich Dmitrishin. Please.
Учасники конференції, шановні колеги, шановні друзі, так, хочеться сказати, що ми вітаємо вас у стінах нашої Одеської політехніки. На жаль, це не зовсім так. Конференція, як вже Володимир Михайлович сказав, проходить у змішаному форматі. Більшість наших учасників далеко від Одеси, але ж все ж таки ми проводимо цю конференцію, ми сподіваємося на плідну співпрацю, на добрі обговорення, на якісь, можливо, і наукові прориви. Ця конференція була започаткована ще в далекому 1991 році видатним професором Анатолієм Грабченко. Проходила вона в мальовничій Алушті, збирала багато вчених і країн минулого СРСР, країн Європи, але ж з відомих причин вже 10 років, як вона проводиться у нашому місті, в Одесі. Ми дуже намагаємося підтримувати всі традиції цієї конференції. Ми скликаємо багато вчених з різних країн світу. Сьогодні, як Володимир Михайлович сказав, що 16 країн світу представлені. Ця географія не тільки Європа, це і Африка, Азія, Північна та Латинська Америка. Володимир Михайлович, Австралія є у нас?
Ні. В цьому році немає, але буде.
Так, сподіваємося, що на наступній конференції ще один континент до нас приєднається. Тому я хочу ще раз побажати плідної роботи. І найголовне, всім нам безпечного неба, миру. На цьому я вважаю конференцію, що можна вважати відкритою, так?
Якщо ви так оголошуєте, то будемо вважати відкритою.
Оголошую відкритою конференцію. Дякую.
До речі, вперше в цьому році в нас є учасники з Латинської Америки, саме з Еквадору, і вони будуть представляти свою доповідь на конференції. And now I invite to speak the co-chairman of the conference, Professor Vitaly Alexandrovich Ivanov. Vitaly.
Good morning. Good morning, Professor Tankanogi. Good morning, our participants. Dear participants, it's a great pleasure for me to speak at the opening ceremony of the InterPartner-2024 conference on behalf of the organizing committee. I am grateful to the General Chair, Professor Volodymyr Tankanogi, for his exciting opportunity. let me say a few words about the conference numbers and facts. The history of this event started in 1991 as a scientific seminar on problems of materials cutting and modern manufacturing processes. It was initiated and created by Professor Anatoly Hrabchenko from Kharkiv Polytechnic Institute. During 1991-2018, the seminar transformed into international seminar and later to the International Conference on Advanced Technologies in Machine Building, and changed the venue from Arusha to Odessa. International Conference on Advanced Manufacturing Processes, founded in 2019 by a team of like-minded.
Vitaly, it is a very bad voice from you.
I'm doing my best.
Okay,
Should
okay. Now good.
Okay. Once again, Grabchenko's International Conference on Advanced Manufacturing Processes, or short name InterPartner Conference Series, is a scientific event founded in 2019 by a team of like-minded persons from Odessa National Polytechnic University, National Technical University Kharkiv Polytechnic Institute, Sumy State University, and International Association for Technological Development and Innovations. It combines a well-known title, InterPartner, adds Professor Grabchenko's name for his significant contribution to materials cutting, and meets current scientific and industrial challenges. InterPartner Conference Series promotes research and developmental activities, intensifying scientific information interchange between researchers, developers, and engineers. InterPartner's motto is "Science unites people together," which means that we can break barriers and drive progress for all through collaboration and innovation. The sixth edition of Grabchenko's International Conference on Advanced Manufacturing Process was now organized in partnership with Poznan University of Technology, Springer, Nature, Authenticate, and International Innovation Foundation. InterPartner-2024 received 141 contributions. After a thorough peer review process, the program committee accepted 73 papers from authors from 16 countries, achieving an acceptance rate of 52%. Thank you very much to the authors for their contribution. 72 members of the program committee and 12 invited external reviewers from 14 countries devoted their efforts and expertise in contributing to reviewing, without which it would be impossible to maintain the high standards of peer-reviewed papers. As a result of their hard work, 300 plus reviews were completed. The full text papers will be published in the book series Lecture Notes in Mechanical Engineering, titled Advanced Manufacturing Processes, selected papers from the 6th Grabchenko's International Conference on Advanced Manufacturing Processes. Now, the InterPartner Conference Series library includes 321 papers, which were downloaded more than 228,000 times and indexed by 838 sources. It's a fantastic achievement for the conference and participants. Congratulations to all of you. The conference includes 2 keynote speeches from well-known and widely recognized scientists, Professor Yuri Vnukov and Professor Alexander Orgian, who focused on the dynamics of machining processes and manufacturing technology. I am sure that their speeches will be helpful to InterPartner participants, particularly those who work within the manufacturing engineering domain. During the conference dates, 73 presentations will be made within 10 technical sessions. We are grateful to our session chairs for accepting the role. Your time and expertise are vital to facilitating a productive and enriching exchange of knowledge. We wish you a great conference ahead. Thank you very much to the InterPartner team. Their involvement, devotion, and hard work were crucial to the success of the conference. Their names are Alexander Sokolov, Maxim Kunitsyn, Anna Balanyuk, Kristina Berladir, and other persons. Thank you very much and enjoy the conference during next 4 days.
Thank you, Vitaly. This concludes our opening ceremony of InterPartner 2024. Thank you all for your participation. The first about 10 minutes. Thank you. Да, начни. So, I am very happy and honored to me provide the first keynote session. Firstly, I would like to present our plan. We have two very interesting and important keynote speeches. At first, will be Dr. Science, Professor Yuri Vnukov from USA. The second will be Dr. Professor Alexander Argyan, Odessa, Ukraine. But at first, I would like to say a few words about Professor Yuri Vnukov. Yuri Vnukov is a well-known scientist in the field of material cutting. His works on the study of contact processes in the cutting zone, the features of the use of wear-resistant coatings on high-speed steel tools are widely known. For many years, he headed the area of work in Zaporizhzhia Polytechnic. Professor Vnukov's works in the field of studying the dynamics of the cutting process, in particular when processing non-rigid parts, are also widely known. For the past few years, Professor Vnukov has been living in Los Angeles, but continues to work with his colleagues from Zaporizhzhia Polytechnic on the study of the dynamic processes during cutting. Now, he is ready to deliver a keynote speech on the following topic: experimental studies of vibration excitation conditions during cutting with cutting tools. Dear Professor, please, you can start.
Dear colleagues, I present to your attention a report on the topic experimental studies of vibration excitation conditions during cutting with cutting tool. The work was carried out by a team of scientists from Department of Mechanical Engineering of the National University Zaporizhzhia Polytechnic, Ukrainian. The topic of the report has been relevant for over 100 years. The problem of vibration excitation during cutting process is not trivial. Science it covers wide variety of cutting types during processing of various parts on machine of various designs. On the other hand, the occurrence of vibration worsens the quality and accuracy of manufacturing parts, reduce the life of machines and tools, creates uncomfortable working conditions for operators, and significantly reduce the economic efficiency of technological operations. Huge practical experiments has been accumulated in a technological method of vibration damping in real industrial production condition. Analytical methods for predicting vibration excitation conditions and the methods for their suppression have been developed and are being improved. However, some physical principles of vibration excitation remain unclear and are used in the form of hypothesis and assumption. No matter how remarkable the proposed theory is, there are only quotation that confirms or refutes its foundation is experiment. The authors of the report have developed a methodology for experimentally studying the physical foundation of cutting dynamics using oscillator, which, depending on the type of cutting, can be either tool or parts. Modern sensor and digital technologies make it possible to measure and record rapidly occurring oscillatory deviation of the oscillator. The data obtained open up opportunities for gaining new knowledge about oscillations during cutting. The report presents the results of experimental verification of the main provisions of the theory of regenerative self-oscillation. The report consists of 4 parts. First, brief historical overview. Second, development of methodology for experimental research on cutting vibration. Third, identification of type of vibration during cutting with cutting tool. Fourth, experimental verification of hypothesis underlying the creation of stability lobe diagram. The works of founders of the theory of regenerative vibration, Plasty and Tobias, defined the boundaries of the vibration stability of machine tools in the coordinates of the critical width of the cut and spindle speed of machine. First, its asymptotic boundary defined the maximum depth of cut that ensures stability at all spindle speeds. Second, its tangent boundary showed the stable region in the low spindle speed zone. Third, its the lobe boundary indicate pocket of stability which are especially effective in the high spindle speed zone. The founders believed that the primary condition for the excitation of regenerative vibration is cutting along the vibration trace, left on the cutting surface from the previous rotation of the part or path of the tool. Moreover, this condition is maintained for all types of cutting, drilling, milling, turning, grinding, across the entire range of spindle speeds. There are 2 points of contention in this theory. Is it valid not to consider the difference between various types of cutting in the mechanism of regenerative vibration excitation? Viewing cutting and abrasive processing, continuous and interrupt cutting is similar. Second, can it be asserted that mechanism of regenerative oscillation, cutting along the vibration trace, occurs at any spindle speeds? This slide presents a typical stability lobe diagram, which is usually divided into a low spindle speed zone up to 3000 RPM and high spindle speed zone. The majority of machine tools operate is a low spindle speed zone. This is due to the fact that increasing the spindle speed or cutting speed reduces the tool life according to the well-known Taylor's formula. The hypothesis underlying the construction of stability lobe diagram are taken from the popular modern textbook Machining Dynamics by Schmidt. Regenerative self-oscillation are observed at any spindle speeds that can reach the values of the natural frequency of the oscillator, as well as under continuous and interrupt cutting condition. The key factor in the excitation mechanism of regenerative self-oscillation is the fast shift of waves on the cutting surface, of adjacent rotation of workpiece during turning, or passes of adjacent teeth during milling. The theory assumes a direct relationship between the remainder of the wall wave over the length of one revolution of the workpiece and the fast shift of adjacent waves. If the remainder is 0, then the fast shift is also 0. The intensity of regenerative self-oscillation depends on the value of remainder. In the remainder is 0.75, minimal stability or maximum amplitude or self-oscillation is observed. The results of the experimental testing of this hypothesis will be presented at the end of the report. In the second part of the report, the methodology for experimental research on regenerative vibration during cutting with cutting tool is presented. The analysis of a principle of coordinate coupling showed the potential to eliminate its influence by creating designs of cutter oscillators with a single degree of freedom. Obtaining oscillograms of cutter oscillator vibrations allows for highly accurate measurement of the main dynamic characteristic related to the cutting conditions and the properties of the elastic system of the oscillator. It's generally accepted that there are 2 main principles defining 2 sources of excitation of regenerative vibration during cutting. First, the principle of oscillation along the x-axis, perpendicular to the cutting surface, cutting along the vibration trace. Second, the principle of coordinate coupling, which depends on the orientation of the stiffness axis of the oscillator K1 and K2 to the direction of the cutting force, as well as the orientation of the stiffness axis K1 and K2 relative to the coordinate system X and Z, where the main cutting motion dr occurs along the Z-axis and the feed motion ds occurs along the X-axis. The experimental results obtained by Tlasty and Kudimov are examined in more detail and presented in general form in Figure 2. The experiments were carried out using a cutter oscillator of length L and rectangular cross-section dimension BH. The cutting edge of the cutter oscillator was located on the neutral axis on the rod at point O. It shows on Figure 1. On Figure 2 shows 5 position of the cross-section of the tool holder relative to the direction of the cutting force. The critical cutting width at which vibration occurs was plotted radially from the origin of coordinates x or z, separately from each case. The Figure 3 shows 5 position of cross-section of the cutter oscillator relative to the coordinate axis x or z. In position 2 and 4, the tool as a cantilever-mounted rod experiences a straight bend, since the direction of the cutting force aligns with the direction of the one of the rigidity axis. With the straight bend, the direction of the resulting displacement aligns with the direction of the cutting force. In the second case, the direction of the force aligns with the axis of minimum rigidity of tool holder, and in the fourth with maximum rigidity. Therefore, in the second case, maximum self-oscillation are observed, and in the fourth, maximum resistance to self-oscillations were observed. In position 1, 3, and 5, the rod of the cutter oscillator experiences an oblique bend. With the oblique bend, the direction of resulting displacement does not align with direction of the force. In the 5th case, the cross-section of the tool holder is located so that direction of the resulting displacement under the action of the force shift. The cutting edge toward increases in the cutting thicknesses. The cutter is pulled into a workpiece and phenomenon called undercutting occurs. It is point that tool cutting edge usually fails. In the other 4 cases, the cutting force pushes in the tool out of the cutting zone during this injection movement. The cutting thickness decreases, which reduces the cutting force. At the same time, during the injection movement, the reaction of the elastic system of the oscillator increases, which, having reached its maximum value, exceeding the cutting force, changes the direction of oscillator movement towards cutting into the material. Thus, an oscillatory cycle of the oscillator occurs. In position 1 and 3, the rigidity axis K1 and K2 align with direction of the axis X and Z. However, in first case, the direction of the resulting displacement is shifted from the direction of the force towards the Z-axis. And in the third case, the resulting displacement is shifted towards the X-axis. Thus, it becomes obvious that a change in the ratio of the cross-section dimension h over b. It is possible to change the direction of the resulting displacement of the oscillator cross-section center O, where a cutting edge is located. This slide illustrates how changing the aspect ratio h over b of the oscillator's cross-section with the size orientation along the x and z axis can change the direction of the resulting displacement of the cross-section center O, expressed as the angle gamma relative to the z-axis. In the equation of the angle gamma that determines the direction of the resulting displacement, there are 2 parameters. First, alpha, the angle of the cutting force relative to z-axis. Second, h over b squared, the aspect ratio of the oscillator's cross-sections. The angle of the cutting force alpha changes a little during cutting and is assumed to be constant. Alpha is approximately 30 degrees. The value h over b squared determines the ratio of the stiffness coefficients of the oscillator's cross-section relative to z and x axis. This slide shows a graph of the obtained dependence of the angle gamma on h over b, based on which three types of cut oscillators were designed. First, cut oscillator Z with single degree of freedom in the direction of the z-axis. Second, cut oscillator XZ with 2 degrees of freedom in the direction of the XZ axis. Third, cut oscillator X with single degree of freedom in the direction of the X axis. By studying the law of motion of oscillators under various cutting conditions, it is possible to study the physical foundation of the cutting dynamics. Cut oscillators allows their dynamic characteristic to be conveniently changed. First, changing the overhang changes the rigidity. Second, adding mass changes the inertial force. Third, changing the overhang and mass changes the natural frequency of cut oscillators. This slide shows the condition of experimental studies of vibration during cutting. In the main series of experiments, longitudinal turning was applied under continuous or orthogonal free cutting, turning a tube, or non-free cutting. These conditions allow the cutting speeds to remain constant for a long time. The deflection of the cutter oscillator from the initial equilibrium position was measured with a displacement sensor, and after digitalization, the signal was stored on a computer. Different signal of cutter oscillation allows the study of vibration include under various cutting conditions. First, cut oscillator X allows the study of vibration during cutting along the trace without the influence of coordinate coupling. Second, cut oscillator Z allows the study of vibration only during clean cutting without the influence of wave generation on the cutting surface and without the influence of coordinate coupling. Third, cut oscillator XZ allows the study of vibration during cutting along the trace in conditions of 2 degrees of freedom. Changing the shape of the workpiece cross-section allows for the creation of continuous stationary and non-stationary cutting, as well as interrupted cutting without different lengths of cutting and idling during one revolution of workpiece. This slide shows two physical mechanisms of excitation of self-oscillation. First, correctly noted in the work of Tobias. They are experimentally confirmed using oscillators X and Z. Then, cutting with cut oscillator X, regenerative self-oscillation are caused resulting in changing in the thickness of the cut. Then the cutting the cutter oscillator Z, self-oscillation are excited as a result of change in the instantaneous cutting speed. Further, all experiments are carried out only with cut oscillator X. This slide shows determination of the vibration characteristic using oscillogram of the cutter oscillator X. It is methodologically important that oscillogram X reflects the exact relationship between the oscillation of the cutting edge and vibration trace on the cutting surface. Then, superimposing the oscillograms of adjacent revolution, it is possible to accurately reproduce the longitudinal section of the cut layer. There, the value of the nominal cutting thickness is set by the feed mechanism of machine. On the oscillogram, it is necessary to observe first the position of the initial equilibrium of the cutting edge before the start of the cutting. Second, the position of the static equilibrium of the cutting edge at any time during cutting. Relative to this position, the cutter oscillator oscillates at idling and during cutting. Third, the initial cutting section is determined by the number of revolutions of the part, its point G, at which the nominal cutting thickness is set. The following are determined from the oscillograms. First, static deflection of the cutting edge. Second, amplitude of oscillation of the cutting edge. Next, cutting oscillator frequency during cutting. Cutting oscillator frequency during idling. Natural cutting oscillator frequency. Phase of waves shift on the cutting surface. Damping coefficient during cutting and idling. And also calculate wavelets on the cutting surface and number of wall waves and remainder on the cutting surface of one revolution of the part. The next part of the report shows the experimental possibilities of studying regenerative oscillations of the cutter oscillator X. First, determination of the type of vibration during turning. Second, determination of stability and suppression of regenerative self-oscillation. Third, influence on the oscillator mass on the change in the dynamic characteristic of the cutting process. The main source of information on the dynamics of the cutting process is the type of oscillogram of the cutter oscillator oscillation. Here are three types of oscillograms recorded during the turning of the part with different cross-section shapes. Turning was carried out under conditions of stable excitation of regeneration safe oscillation. First, when turning around part, the oscillogram shows gradual excitation of vibration from beginning of the cutting to point G, and then the oscillation remains stable for a long time relative to the static equilibrium position. Second, then turning of round part with groove, interrupted cutting is observed, where at moment of passing the groove, there is no cutting, but the oscillator continues to oscillate relative to the initial equilibrium position. During the cutting, the cutter oscillator oscillates relative to the static equilibrium position. Third, then turning apart with short protrusion, interrupted cutting. The cutter oscillator oscillates then cutting relative to the static equilibrium position, and then idling relative to the initial equilibrium position. It is quite obvious that each case a different picture of the vibration process is observed. However, in all these cases, the size of the initial cutting section, determined by point G, remains unchanged and equal to 5/6 revolution of the part. This indicates that with unchanged cutting modes and dynamics characteristics of the elastic systems of the oscillator, the considered types of turning do not affect the number of revolutions of the part after which steady cutting is observed. The results of experimental determination of the point G with changing in the cutter oscillator rigidity and cutting modes are shown here. First, with the increase in rigidity, decrease length of cutter oscillator, the initial cutting section is significantly reduced, and with absolute rigidity of the cutter oscillator, cutting to the nominal cutting thickness would occur in one revolution of the part. Second, changing the cutting speed in the range from 100 to 300 meters per minute does not have a significant effect on the point G of the completion of the initial cutting section. Third, increasing the cutting thickness or increasing the feet strongly reduce the length of the initial cutting section. Fourth, increasing the width of the cut or increasing the depth increases the length of the initial cutting section. Since vibration during cutting always occurs relative to the position of the cutter oscillator's static equilibrium. Knowledge of the law of change in the position of static equilibrium is the basis for considering the dynamic of cutting. The position of the oscillator's static equilibrium determines the magnitude of the static deflection Bx from the initial equilibrium position at each moment in time. Conventional dynamometers determine the static cutting force by the deflection Bx of the elastic element. Figure A shows the change in the dimension Bx at each revolution of the part in the initial cutting section during continuous turning. The highest rate of the change, delta Bx1, is observed on the first revolution, and then the rate of increases, delta Bx2, delta Bx3, and other, decreases to point G. In the steady state section, the value of Bx remains constant. What is important here is that a large increase in the rate delta Bx1 is observed on the first revolution, which determines the rate of growing of the force applied to the cutter oscillator. In the theory of oscillation, the case has an analytical solution. Then the linear increase in force with a certain rate causes excitation oscillation in the cutter oscillator. Thus, with continuous stationary cutting starting from the second revolution, the cutting already continues along the vibration trace left of the first revolution. So, at the second part revolution, two force sources act the cutter oscillator. linear increase in force with growing rate delta bx2, and harmonic force from cutting along the trace. At the section of steady cutting and part revolution, the linearly increasing force disappears, and there is only one source of oscillation, the harmonic force from cutting along the trace. The oscillogram of cutter oscillator oscillation shows a stable self-oscillation at the end turn of the workpiece. Let us consider turning a part with groove at the first two revolutions. At the first revolution, the value of bx increases with the rate delta bx1 until the cutter oscillator cutting h enters the groove. At the moment to entry into the groove, the cutting force is called by bx equal 0, but the cutter oscillator continues free oscillation relative to the position of initial equilibrium. At the beginning of the second revolution, there is an instantaneous application of cutting force. Thus, three force sources of oscillation excitation are observed on the second revolution of the part. First, instantaneous application of force with the value of bx1. Second, linear grooving of the force with the rate delta bx2. 3. Harmonic application of force during the cutting along the trace. Naturally, these forces are influenced by inertial force and damping forces. But there is a mixed system of the force that act simultaneously on the cutter oscillator during one revolution of the workpiece. At end turn of the steady cutting, the linear grooving of the force delta bx disappears, but the other force sources continue to act on the cutter oscillator. The oscillogram of cutter oscillator oscillation at end revolution during turning a part with groove is shown in figure B. After plunging cut, the maximum deflection of the cutter oscillator has damped character in the initial cutting section. This is followed by a turning section of the regenerative self-oscillation, and then a section of steady self-oscillation is observed. Then a blade enters the groove. Free damped oscillation are observed during the idling. Then cutting a part with protrusion. The force loading conditions have a different pattern. Of the first revolution of the part, there are short plunging cutting section with a force bx0 and a long idling section. On the second revolution, the plunging cutting force on the short cutting section is equal to delta bx1, which is momentarily removed during the idling. At each subsequent revolution, the plunging force delta bxn increases to constant value delta bx in the initial plunging cutting section. The oscillogram of cutter oscillation deflection at n revolutions of steady cutting is shown in figure C. It consists of two sections: dampened oscillation after plunging cut into the short protrusion and dampened free oscillation during idling. In this case, it is extremely important to note that there are no conditions for the excitation of regenerative self-oscillation at short cutting leads. Similar cutting condition can be observed in the end milling with a small radial depth of cut. Then only one tooth cut and there idling the work of the adjustment teeth. Based on the results of the experimental analysis presented on slide 17, a scheme of vibration types induced during turning can be proposed. The motional law of oscillogram of oscillation of cutter oscillator is determined by condition of its force loading. Each loading condition corresponds to its own motion law of the oscillator. During turning, four types of force loading of the cutter oscillator have been identified. First, linear application of the increasing force with each revolution at the initial cutting section with induced free accompanying oscillations. In the first revolution of the workpiece, there are primary vibration. Second, instantaneous application of constant force during the plunge cutting in each revolution of interrupted cutting. During the steady state cutting section with induced damping free accompanying oscillation. Third, instantaneous removal of force during the idling section induced damping free oscillation of the cutter oscillator. Fourth, harmonic application of force Starting from the second revolution of the workpiece during cutting along the trace, induce regenerative self-oscillation. The harmonic application of cutting force under non-stationary cutting condition induce forced oscillations. For each type of cutter oscillator force loading, there is analytical solution to the law of its motion over time. The possibilities of using a cutter oscillator to study the stability of regenerative self-oscillation are shown. During continuous non-stationary turning of the part installed in an eccentric chuck, conditions are created for forced oscillation with a part rotation frequency omega f. At a certain cutting speed, regenerative self-oscillation with a frequency omega n close to the natural frequency of cutter oscillator begin to be excited simultaneously. Self-oscillation are superimposed on forced oscillation and remain stable for a long time in a certain speed range. Then, leaving the excitation zone self-oscillation, they dump, but forced oscillation are observed at all cutting speed. There is a defect hole on the machine surface that causes a random heat of cutting force, then stable self-oscillations, having passed the setting up section, are quickly restored. An increase in the wear area of the flank surface of the cutter leads to extremely superation of the cessation of self-oscillation. Oscillograms of cutter oscillator deflection are given when turning a part with groove with an increase in the wear area on the flank surface of the cutter, a decrease in amplitude of self-oscillation with an increase in HB to 0.3–0.4 mm, associated with increase in volume of deformation of the material being processed by the wear area in the cutting section AB, which leads to decrease in the depth of cutting edge penetration into the allowance. It was previously stated that the cutter oscillator allows changing the rigidity by changing the overhang legs, as well as adding mass to the cutter head. These capabilities make the cutter oscillator a universal tool for studying the dynamic of cutting. The slide presents the results of experimental studies of the effect of the added mass of the cutter oscillator on its behavior during cutting. Here, M0 equals 0 is a cutter without added mass, M1 equal 102 grams, M2 equal 344 grams is the added mass. Then added mass under unchanged cutting conditions. First, the frequency of regenerative self-oscillation decrease significantly, but exceed the frequency of natural oscillation during idling by 15–20%. Second, the amplitude of regenerative oscillation increases. Third, the static deflection Bx does not change significantly. The fast shift of adjacent waves fluctuates in the wide range from 65 to 130 degrees, but does not change significantly than adding mass. This part of the report is devoted to the experimental verification of the hypothesis underlying the creation of the SLD for the low-speed spindle zone. The following were investigated. First, the excitation boundaries of regenerative self-oscillations. Second, the influence of spindle speed on the intensity of self-oscillations. Third, the relationship of the remainder of the wall wave with the fast shift. Fourth, the influence of fast shift values and the remainder of the wall wave on the amplitude of self-oscillations. For a machine tool, the main characteristic of motion are spindle speed and feet per minute. For the cutting process, the characteristic of motion are cutting speed and feet per revolution during turning or feet per tooth during milling. Therefore, the cutting, it is pointless to consider the spindle speed without the diameter of part or diameter of tool. In this case, vibration excitation should be studied when changing the cutting speed. Depending on the type of processing, the range of working cutting speeds can be quite wide. From minimum during linear motion of planing, broaching to maximum, then limitation of which is a tool life. The slide shows the zone of regenerative self-oscillation begins behind the zone of degeneration of build-up. With increasing speed, the intensity of self-oscillations increases, reaches a maximum to critical speed, and gradually decreases until complete disappearance. A high speed, a zone of vibration-free cutting, is observed. However, the transition to the vibration-free cutting zone, high speeds, it's possible only when cutting aluminium and other easy-to-cut materials, or using tool materials with high heat resistance. For example, cubic boron nitride, heat resistance of which 1600 degrees. In the regenerative vibration zone, first, the average frequency of self-oscillation remains constant with a small range. Second, the wavelength of the cutting surface increases proportionally to the speed increase. The effect of the cutting width, cutting thickness, and rake angle on the intensity of self-oscillation is shown in speed coordinates. These dependencies were first established by Kuchma in 1948 and became classic, included in textbooks. Here, increase in cutting width increases vibration, and increase in the cutting thickness and positive rake angle suppress vibration. The amount of wear of flank surface has an exceptionally strong effect of vibration suppression. In longitudinal turning, it is easy to create conditions when cutting at constant cutting speed. Turning can be performed at different spindle speeds, changing only the size of the part diameter. The purpose of the experiment to determine the effect of the spindle speed on the intensity self-oscillation under condition of maintaining constant cutting speeds of 150 meters per minute at which intense self-oscillation are excited. The spindle speeds varied from 362 to 1836 per RPM, which changed the diameter of the part from 132 to 26 millimeters. A cutter oscillator X with additional masses was used. 0 grams, 102 grams, 344 grams. A total of 152 experiments were conducted, the results of which are presented in the form of scattering diagrams. Conclusion: the spindle speeds does not have a significant effect of amplitude of self-oscillation in the range of the spindle speed variation. In the zone omega is when 100 revolutions per minute, causes of amplitude decrease were observed. Another way to experimentally check the influence of spindle speed on the excitation of regenerative self-oscillation can be turning the disc with a cutter oscillator X. Turning a disc with diameter of 32 mm to 130 millimeters with one spindle speed at each moment to time increases the cutting speed. Then the speed the mean is reached, regenerative self-oscillation of the oscillator begin to be excited, leaving the vibration trace on the machining surface of the disc at the diameter d mean. With continued cutting, the vibration trace disappears at the diameter of the disc at the speed Vmax. Loss of vibration pattern between diameter d mean and d max remains of the machined surface. The cutting speed V critical at which the vibration intensity is maximum is determined on average diameter of this stripe. Repeating this experiment at spindle speeds 300, 400, 550, 700 RPM showed the location of vibration stripes on different disc diameters. The results of the experiment are summarized in a table and shown in the slide. Conclusion: the appearance of the regenerative self-oscillation zone does not depend on the spindle speed, but is determined by the cutting speed. Both series of experiments allow us to state that then, considering the dynamics of cutting process, the main characteristic determining the vibration intensity is the cutting speed and not the spindle speed. In this regard, there is a doubt about the correctness of using SLD to access the vibration stability of various types of cutting in the low speed zone. During the main series of experiments when longitudinal turning was performed at a constant cutting speed by simultaneously changing the spindle speed and the diameter of the part, unusual similar irregularities were observed between the spindle speed and the frequency of self-oscillation, as well as between the spindle speed and the phase shift of adjacent waves. If the experimental points obtained for oscillators with different additional mass are placed in the coordinates psi and FSO, then in all cases a close correlation relationship is obtained. The discovered phenomenon of a close relationship between the values of psi and FSO possibly reflect the conditions of self-organization of the cutting process as a dynamic system. The most important hypothesis of the theory of regenerative oscillation is the relationship between the magnitude of phase shift of adjacent wave and the intensity of self-oscillation. Moreover, the phase shift of waves is associated with remainder of the wall wave, then lying wall wave on the length of the cutting surface on one revolution of the part with diameter d. This hypothesis is very to verify experimentally. Knowing of wavelengths on the cutting surface, it is possible to determine the number of wall waves and the remainder for each diameter at which the intensity for self-oscillation is studied. Figure 1 shows the distribution of the calculated number of wall wave and the remainder for cutting with cutter oscillator with different additional masses, M0 and M1, for each experiment, each diameter of the part. Different in this distribution patterns are associated with different wavelengths on the cutting surface. Figure 2 shows the distribution of wave reminders for each experiment, each spindle speed. Figure 3 shows the distribution between the experimentally measured values of psi and the calculated value of the remainder. Conclusion: there is no correlation between the calculated waves of the wave remainder and the experimentally measured values of psi. Figure 1 shows the scatter diagrams of the calculated values of the remainder and the experimentally measured oscillation amplitudes AX. There is no correlation for cutter oscillators with different additional masses. Figure 2 shows the scatter diagrams of the experimental values of the wave's shift phase and the amplitude of the self-oscillation AX. There is no correlation for cutter oscillators with different additional masses. However, at psi equal 90 degrees, a decrease in the amplitude values is observed. General conclusions are given on slides 30 and 31, which can be read in detail, but in short the following can be noted. First, original designs of cutter oscillators with single degree of freedom along the X and Z axis have been developed which allow studying the cutting process only by the vibration trace or only by the clean one, without the vibration trace, in the absence of coordinate coupling. A methodology for studying vibration by the oscillograms of cutter oscillator deflection has been developed, which allows studying and formulating the physical foundation of the dynamics of cutting with a cutting tool. An experimental test of the hypothesis underlying the theory of regenerative self-oscillation, on the basis of which SLD were created, has been carried out. The experimental results have shown that for the region of low spindle speed, none of the proposed hypotheses has received experimental confirmation. The phenomenon of the close relationship between the frequency of regenerative oscillation and the phase shift of adjacent waves has been established. Perhaps this connection determines the conditions of self-organization of the cutting process during vibration as a dynamic system. The literature referenced in the report is provided. The authors will gratefully accept critical comments and suggestions on the materials of the report. Thank you for your attention.
Thank you very much for your interesting speech, Yuri Nikolaevich. Maybe some questions from
many questions. I am ready to answer, but only Russian, please. Please. You understand me?
Будет прямой переписки.
Да. Есть мой электронный адрес. И все вопросы можно задать по адресу, и я с удовольствием всем отвечу.
Вы только в WhatsApp, да?
Сейчас я не в WhatsApp, сейчас я с вами на конференции, да.
Володимир Михайлович, в Ютубі питань немає. Можливо, від вас буде.
No, we have one question from conference hall. No? No. We have no questions. Thank you very much, Yuri Nikolaevich. Next, our speaker is Alexander Orgyan, Doctor Science Professor in Odessa Polytechnic. Professor Orgyan has been working at Odessa Polytechnic for many years. He is widely known for his works on fine-tuning and boring. With these finishing methods of processing, dynamic processes have a great influence on the accuracy of processing, to the study of which Professor Orgyan and his colleagues devoted a lot of time and obtained interesting results. Topic of his speech is non-stationary dynamics of machine tools, computational and experimental analysis of stability and oscillations. Please, Alexander Andreevich, you can start.
Dear conference participants, we would like to draw your attention to the report under the general title Non-Stationary Dynamic Systems of Machine Tools, Computational and Experimental Analysis of Stability and Oscillations. Let me begin with some comments. We consider the dynamic system of the machine tool as a multi-lobe closed system, the elements of which are the classic system and the working processes. They allows of advanced mathematical methods of the theory of automatic control to study stability, calculation, self-oscillations, and forced oscillations. This approach introduced the concept of the dynamic quality of a machine tool. The problems of machine tool oscillations with variable parameters of the dynamic system have been studied the least. Such systems are called non-stationary, and the oscillation are called parametrics. For example, the following no-station problems of machine tool dynamics have not fully solved. 1. Cutting along a trace. 2. Rotation of the cutting zone, rotation of the cutting force. 3. Variability of cutting. 4. Variability of the rigidity of classic system. Variability of feed rate. 6. Interaction of the cutting process, etc. In all these cases, the stability of the system and the characteristics of the oscillation should be studied. Introduction and major challenges. When multi-spindle machining of procession surfaces, the sources of excitation, of vibration, and the main patterns of their influence on the machining accuracy have not been studied. There are also no experimental and theoretical dependencies of the magnitude of errors of the level of forced vibrations in the classic system of multi-spindle machine tools. It should be noted that the current level of precision requirements for multi-spindle machining cannot be reliably guaranteed by conventional technological solutions. For example, optimizing processing modes and tool geometry, lightening the parameters of spindle heads with boring bars, reducing temperatures, deformation, etc., without taking into account dynamic phenomena arising during the transmission of disturbances from the spindle to another. Based on the study of the influence of spindles, combined operation of the characteristic of accuracy, productivity of finishing boring machines, the purpose and objectives of the research were determined. Aim and research tasks. The purpose of the work is to study the accuracy of fine boring during the combined operation of spindles of finishing and boring machines. To achieve this goal, the following tasks have been set. 1. Determine the static and harmonic influence coefficients when two spindle heads operate at the same time. 2. To study deviations from roundness, waviness, and roundness of bore surfaces when operating 1, 2, and 3 spindle heads of different size and different stiffness diagrams. 3. Investigate the mutual influence of spindles with two rotation drive schemes. They increase the productivity of finishing and boring machines, as well as the tendency to concentrate operations, have necessitated the installation of several spindle heads of the same or different size on the bridges of finishing and boring machines. An analysis of the machines designed in Pivden-West statement shows that the number of multi-spindle machines is more than 85% of the total, with most machines equipped with 2 or more spindle heads. Research methodology. Disturbances transmitted from the one spindle to another and their changes per spindle revolution can be described by static and harmonic influence coefficients. The static influence coefficient, as well as the static influence coefficient for multi-cutter boring, is determined by the movement of the axis of the control mandrel mounted on one spindle under the action of a unit force statically applied to the other spindle head and changing in direction. The harmonic influence coefficient is determined by the amplitude of the state force oscillations of the axis of the control mandrel installed on one spindle head under the action of a unit harmonic sinusoidal force applied to the other spindle head and varying of frequency and direction. The experiments were carried out on the basis of a finishing and boring machine model 2070B. In the first group of experiments, the static and harmonic influence coefficients were determined were transmitting disturbances between two spindle heads. The diagram of the experimental stance is shown in Fig. 1. The static influence coefficients were determined as follows. A force F 2000 Newton was statically applied to the spindle head flange 1. The direction of force F varied from 0 degree counted from the vertical plane to 180 degree in increments of 30 degree. In this case, the corresponding moments of the axis of the control mandrel mounted on the measuring spindle head 2 were measured. The displacement measurement planes are shown in Fig. 1. The harmonic influence coefficient of were determined in a similar way. However, the disturbing force F 2000 Newton created by a vibrator change not only in direction but also in frequency. Determination of static and harmonic influence coefficients was carried out with non-rotating spindles, and the rotation was simulated by changing the direction of action of the force F. In the second group of experiments, the deviation from roundness and the roughness of forward holes were determined during the operation of 1, 2, and 3 spindle heads of the first and second standard size. The spindle heads were equipped with single cutter boring bars L2D1 and L2D3, L length, the diameter of the boring bar. When boring with two spindle heads, the mutual influence of the spindle was also studied with two rotation drive schemes. Figure 2, workspace made of steel C41 and etc. At the same time, deviations from roundness and roughness of the board surface were determined using boring bars with different compliances installed on the same spindle head. The second head, used as a source of vibration, did not work. At the second stage, boring was carried out with the first spindle head while the second one rotated idle. At the third stage, boring was carried out with two simultaneously working heads. Results. Figure 3 shows the values of the static and harmonic coefficients of influence of one spindle on another. It can be seen that the maximum static influence coefficient is achieved when the force F is in the vertical direction, and the minimum is achieved when the force is horizontal. When measuring the harmonic influence coefficients at the natural frequency is oscillation of a spindle with a mandrel, the disturbances are most intensively transmitted in the direction of the force, which is close to horizontal minimum compliance of the system, and in the low frequency range the disturbances are transmitted in the vertical direction. This phenomenon becomes understandable if we consider the machine's supporting system as a vibration isolation based on which interacting spindle units are installed. The maximum efficiency of vibration isolation is achieved with the greatest flexibility of the base. The depends of the static influence coefficient on the direction of action of the force leads is changes in deviations from the roundness on the machine whole. The harmonic coefficient is of influence on the spindle on cleanliness mainly determines the waviness of the cross section of the boring hole. The circular diagrams show the change in waviness according to the angle of rotation of the spindle. Figure 4. The resonant properties of the system were manifested in the fact that near natural frequencies, the values of the harmonic influence coefficients are an order of magnitude greater than the values of the static influence coefficients. This work investigates the error caused by the influence of simultaneously operating spindles of the finishing boring machine. This error is additional to the error caused by elastic deformations and calculated according to the method described on the slides 9 and 8. The dynamic component of the deviation from roundness caused by the interaction of the spindles can be determined by the value of the maximum dynamic disturbance and the value of the harmonic influence coefficient at a frequency of maximum dynamic disturbance. Equation 3. From the experiments, it follows that each spindle can comes into operation reduced the accuracy characteristics by 10–15%. In conclusion of the first part, I would like to emphasize some important points. Note that the obtained values of the coefficients are much more accurate than the calculated ones due to the complexity of developing a dynamic model of a spindle machine. The reason for the significant difference of the reps of static and harmonic influence coefficients is that the static coefficients characterize the basic completion of the elastic simple system of the machine, and the harmonic influence coefficients characterize dynamic components. That's the change in values when the frequency of the pairing force changes. In this case, the mutual influence of the spindles depends on the direction of action of the disturbing force and the dynamic compliance of the supporting system. State influence coefficients from deviations from the roundness of bored holes and harmonic influence coefficients form waveness. The harmonic influence coefficients change depending on the damping effect of the load-bearing elements of the machine, and the greater the rigidity of the load-bearing elements in a given direction, the less the damping action and the greater the harmonic influence coefficients at the natural frequency of variation of the spindle with the tool. With the existing design of the main notion drive, each spindle that comes into operation again deteriorates the boring accuracy by an average of 10–15%. Main recommendation: the effectiveness of research in the field of dynamics of technology systems is ensured by deep knowledge in the field of the theory of mechanical vibrations. Taking this opportunity, we note the latest research on the dynamics of fine boring during intermittent cutting. Fine boring is a finishing operation, is often performed on holes with an intermittent surface. Such a surface is formed in the presence of grooves, recesses, and also in intersections of the processed whole with others. The periodic repetition of the tools entry and exit is an additional disturbing factor causing higher oscillations during intermittent cutting than during continuous cutting. The discontinuity of the machined surface leads to a periodic break in the connections between the elements of the machine system. Therefore, a closed dynamic system becomes a system with variable characteristics. If the equilibrium state of such a system of disturbed, then particular oscillations with AQ, they cannot be called free signs of the parameters of the system periodically change, but they cannot be called forced signs. An external action does not represent a disturbing force, but is part of the equation of motions. Such dynamic systems in which oscillations is excite amplitude by changing their parameters are usually called parametric oscillatory systems, and the oscillations are called parametric. In some areas of excitation frequencies, the amplitudes of parametric oscillation increase monotonically. A phenomenon of parametric resonance is more dangerous than ordinary resonance, which occurs only at one frequency of the disturbing force and under any initial conditions, including zero. Parametric resonance occurs at an infinite number for excitation frequency values as a result of occurrence of inevitable axial disturbances. In this case, the ratio of the oscillation frequency to the frequency of change of parameter P2 omega can be called 2, 1, 2, 2, 1, 3, 2, 2, etc. The definiting feature is closed dynamic machine cutting system during such processing is the non-stationary of the system under study, namely closed and open state alternate in time due to periodic interruptions of cutting process. This the dynamic system of the machine tool is affected by parametric disturbances, the discontinuation of the machine service also leads to external effects on the working processes, change in settings, periodically repeating at the moments of cutting in and out. The named features of the dynamic system under study lead to the fact that the loss of stability in it can occur not only due to the presence of feedback but also due to the periodic change of parameters. Figure 6.1. Non-stationary of described by mounting the outputs of stationary links by a piecewise contact periodic function F2 to the period of change of which is no greater than the period of rotation of the spindle. On number 4, a quotient of motion in the direction of the principal also, where f from t is the time function of the period, determined for the case of equally spaced grooves by the following relations. It is important to note that the adapted dynamics models and equations of motion only reflect the level of our knowledge and are adapted with some assumptions. Equivalence of model 6.1 when considering oscillations along the coordinate and applying the Euler substitution. After transformation, we obtain Hall's equations. 5. The stability conditions of the system and obtained by the stiffening method taking into account of periodical conditions. The calculation of stable solution are presented in the Einstein diagram. Figure 6. Einstein diagram. The diagram shows shaded area of stable solutions. This acknowledges the parameters of the elastic system and the cutting process. We can determine the stability of the closed dynamic system of the machine. This is great. What else is there to investigate? Life analogy areas. We know a person of absentia, but we do not recognize him on the street. The time form of oscillations is not known from the diagram. Their features, patterns, and difference are not known. The amplitudes and other parameters are not known, especially in the calculation plan. Therefore, our research was aimed at the possibility of analytical calculations of oscillation parameters and establishment of other time forms. Calculation programs were developed and their results were compared with experimental data. The calculation in one program was carried out in the Simulink computer simulation software environment integrated into the Universal Computer Mathematics System MATLAB, and the other calculation was carried out in the MATLAB environment with certain requirements for determining the initial conditions during the transition from cutting to free oscillations. It was found that the calculated time forms of oscillation correspond to the experimental ones. The nature of oscillation was determined against the background of periodic change in the state of equilibrium and the moments of cutting and exit of the cutter into the groove. High frequency oscillations are also excited. The decrement of oscillation during cutting differs from that measured when passing the groove and can be expressed through a parameters of closed dynamic system. It should be noted that immediately after cutting, the oscillations are of a decremental nature even under such processing conditions that when boring solid surface lead to the excitation of self-oscillations. This is explained by the cytoprism effect of the impact pulses during cutting, due to which the oscillations on two successive revolutions are almost in phase, and the cutting measurement along the trace stabilizes the closed dynamic system. As the cutting depth increases, the sheet in the equilibration position cutter release increases, and the initial values of high frequency oscillations amplitudes are also increased. The maximum values of the oscillation amplitudes when boring a discontinuous surface are 2-4 times greater than when boring a continuous surface, and the minimum values are the same as where there are intersection. Some experimental results are shown in the following figure 7-8. On this slide, you can see the figure from 9 to 12 show the calculated time forms of oscillation. Signs of dynamics of intermittent cutting determined by the ratio of the natural frequency of the system to the frequency of the disturbance and dependence of the amplitude of oscillations on the rigidity and mass the elastic dissipative inertial system also turns out to be non-monotonic. If the cutting speed control is for some reasons irrational, it is positive to remove the dynamic system from the dangerous resonant region by changing the natural frequency. For example, by increasing or decreasing the mass of the free end of the cantilever boring bar. It should also be noted that the problem of vibration damping during intermittent cutting has been investigated. A special boring bar with increased torsional complaints have been developed, ensuring a reduction of the vibration level. The resonance value of the vibration amplitudes of torsional flexibility boring bar are from 1.5 to 2 times less than those of conventional rigid boring bars. In conclusion, I would like to express my gratitude to my colleagues for participating in this research. Professor Gennady Aborsky, Professor Viktor Khobin, Professor Ruslan Matsey, Professor Vladimir Tonkanogy, Professor Vitaly Ivanov, Associate Professor Anna Balanyuk, Associate Professor Vladimir Kobelev, Associate Professor Vasily Kolesnik, Engineer Pyotr Trifonov, and postgraduate student Alexander Badovsky. Thank you for your attention. Dear conference partners,
For your interesting speech. Maybe some questions in conference hall. Oh, Professor Larshin, please.
It was a very interesting report and representation. I should like...
Please slowly.
one question about influence coefficients. You have said about influence coefficient. About determine the influence coefficient, static and harmonic. Tell me, please. Influence coefficients. Determining of these coefficients. Thank you.
Thank you.
Thank you.
Please, Alexander.
You can see on diagram of the experimental stem, and you see this on slide 1. Figure is figure 1, and your question is very important for this oscillator, this report, because it is very often used for design of machine tools. The static influence coefficient was determined as follows: a force 2000 Newton was statically applied to the spindle head number 1. The direction of force F varied from 0 degree from the vertical plane to 130 degree to increment of 330 degree. In this case, the corresponding machines of axis of the control mounted on the measuring apple head two were measured. The placement measurement plans are shown in Figure 1. The harmonic influence coefficient in H12 were determined in a similar way at the same time. However, the disturbing force F equal 2000 Newton
Владимир Михайлович, вы меня слышите?
by
Hello.
the vibrator changing, not only in direction but also in frequency. The determination of static and harmonic influence coefficients was carried out with non-rotation spindles, and the rotation was simulated by changing the direction of a situation of the force 200 Newton.
Владимир Викторович,
It's so.
Okay, thank you very much.
Yes.
Thank you, Alexander Andreevich. Maybe have any questions in YouTube? No? No. Thank you, Alexander Andreevich, for your interesting speech. And now, according to program, a break is announced for time for lunch until 1 o'clock past meridian. Thank you very much for participation.
we can start.
Okay, thank you. Hello for everyone. Welcome from Poznań University of Technology. My name is Olaf Ciszak. I very happy to see you and to hear in the conference InterPartner 2024. Thank you for the organizers, especially for the Vitaly Ivanov, the co-chair, and thank you for the rector of Odessa Polytechnic National University, Professor Gennady Oborski, and of course for the general chair of the conference, Professor Vladimir Tulkanoy, for the invitation for the conference. In great pleasure, I take the invitation, and at this moment, I think we should start our session first. In the subject of design engineering. Please, all the presentation will be on the YouTube channel. At this session, we will have the seven presentations, and in the book of abstracts, you can find the additional six articles with the area of design engineering. My dears, I think we can start, and at this moment we should reconnect to the YouTube channel. And after that will be the question session, of course, the discussion of each of the presented materials from the area of designing engineering. Okay? Yeah, Vitaly, I forgot maybe something. No.
Everything correct. Thank you.
Okay, let's start. Please, Alexandre.
The topic of the article, heuristic analysis of the accident on the ship's rudder propeller columns. It is case study. Based on analysis of marine power system carried out by the Swedish club, 19% of faults are related to transmission of various types and purposes. Investigating the causes of marine transmission accidents is a highly complex task. In addition to the usual causes of accidents, poor quality elements, imperfect installation or overloading, the action of the crew, and weather factors must be considered. To establish the causes of an accident, it is not enough to carry out the appropriate calculation. In most cases, this is a heuristic task. Accidents on the fire ship followed a similar scenario. Accidents associated with the failure of one of two rudder propeller columns. Some vessels were forced to go to the nearest port for repair. The degree of faults was different, but the type of faults was similar. It was necessary to study the cause of the accidents. Each vessel has two rudder propellers. The rotation of the propeller allows the vessel to move. The rotation of the column body changes the direction of the vessel. In emergency condition, the vessel can move with one working rudder propeller. In this picture, you can see the design of Rolls-Royce rudder propeller columns. Three main units in this design: upper bevel gearbox A, gear coupling unit B, and lower bevel gearbox C. Shaft 1 on the upper bevel gearbox installed in bearings 2 and 3. Through 2 and 3. A pinion 4 is installed on the shaft, which engaged with a gear wheel. 5. The wheel shaft is placed vertically in bearing 6 and 7. The rotation from the low-speed shaft of the upper gearbox 8 is transmitted through the gear couplings 9 and 10 to the high-speed gear shaft of the lower gearbox 11. This shaft is mounted in bearings 12 and 13. Rotation from the vertical shaft is transmitted to the horizontal shaft of the propeller. The pinion 11 is engaged with the bevel wheel 14. The wheel shaft is installed in bearing 15 and 16. Seal 70 prevents seawater from entering in the housing of lower gearbox. Lubrication of the gearbox and gear coupling is carried out using a gear pump. The vertical shaft 11 of the lower gearbox is long and heavy. In this picture, you can see examples of the damage of elements of column. Left horrible pitting on the rolls of bearing, then pitting of rear coupling, and right pitting of bevel gear tooth. And this slide, the picture of damaged elements point out at the right position accordingly to the design of lower gearbox. Usually, the lower gearbox elements has been most fouled. The two surfaces of pinion A and wheel B have signs of progressive pitting. In particular, this applies to the surface of pinion teeth. On some teeth, the pitting area was up to 20% of the working surface of the tooth. The surface of the rings and the rolling bodies of the bearing also have traces of progressive pitting. Shown is the pitting of the inner ring of the tapered roller bearing F, which carries the main axial forces in adjustment. Some rollers were completely destroyed and metal chip were removed from them. To found the root cause of the fault, the engineering calculation was performed. Geometrical parameters that are known, number of teeth, module, tooth widths, helix angle. In addition, it was found outer cone distance, outer transfer module, outer pitch diameter of pinion and gear. Since the found module is not standard and does not have closer standard values, it is assumed that the gear train is designed in accordance with the standard ANSI IGMA. It is calculated transfer diameter pitch closer to standard 1.5 inch. We use the program MechSoft to check the assumption made. You can see print screen of the geometrical part of this program MechSoft. Engineering calculation of bevel gears using equivalent cylindrical gears have been performed. It is shown that the safety factor is less than permissible value specified in the register of shipping, 1.55. This means that the root cause of the accident is the poor design of the Rolls-Royce rudder propeller cone. Rolls-Royce rejected this conclusion, as it was based on the outdated approach, and turned to Klingelberg for help. They calculated the maximum contact stresses using the finite element methods. It was less than the allowable one. With the help of the finite element methods, the contact stresses we also investigate, taking into account the deformation of the bearing nodes. The maximum contact stresses were also lower than permissible. A situation arose when calculation performed using one method were opposed to calculation performed using another method. A similar situation occurred with the calculation of bearing units. Accidents of fire ships followed a similar scenario. To solve the problem, it was decided to use the heuristic method based on the similarity of the scenario. The design structure matrix was compliant, which takes into account the interaction of all elements. The vertical and horizontal numbers are the gearbox element numbers. They corresponded to the position in slide 5. The sign union means that the parts are in contact. The sign anchor indicates that damage to one element leads to damage to another element. Inside the rectangles marked with bold lines are the elements included in the assembly. Elements are divided into 4 groups. Undamaged elements are marked in green. Elements whose performance is limited by time are marked in yellow. Elements that have limitation according to certain parameters are pink, and elements which need to be repaired in factory conditions are red. Thus, a morphological matrix of damage is superimposed on the DSM matrix. Such a combined DSM morphological matrix gives a more visual representation of the possible causes of the machine destruction. Using this matrix, you can visualize the process of damage propagation in the transmission. The resulting picture of the damages spread makes it possible to exclude one of the first version, being considering that the cause of the accident was the ingress of seawater into the lower gearbox housing. In this case, the most damaged elements would be bearing 16 and the bevel train of lower gearbox. A version of pitting of the two surfaces of the upper and lower gearbox was also considered, which was not progressive and initially did not pose a danger, but led to contamination of the lubricant with metal dust, which intensified the pitting process. In this case, the pitting of the gear teeth of the upper and lower gearbox, as well as the bearing, would be more uniform. Based on the analysis of the resulting matrix, it is obvious that the root cause of the accident was the destruction of the spherical roller bearing 13 due to a combination of number of factors: thermal expansion of the shaft bearing, deformation, and a change in the load distribution in the bevel gear meshing. Conclusions. An analysis of the design of rudder propeller cones and methods for calculating marine transmission was carried out. The assessment of the loading capacity of transmission can be conducted on the basis of generally accepted standards and on the basis of the rule compliant in the register of shipping. In turn, numerical simulation of processes in meshing using the finite element method has de facto become a standard. These calculation methods are not the same, and when investigated in accidents, a conflicting situation arises regarding the assessment of the load capacity of transmission's elements. Analysis of the failure causes of marine transmission is very important from a methodological point of view. Numerical calculation methods make it possible to create gear trains models closer to real ones. The basis of ANSI, ISO, and DIN standards, as well as register of shipping, are traditional calculation methods that reproduce outdated approaches. However, these calculations are based on the experience of designing, manufacturing, and operating transmissions accumulated over decades. A method has been developed that allows, based on analysis of the transmission design and identified damage to its elements, to search for the causes of an accident. This method is based on superposing the morphological matrix of damage on the design structure matrix. The combined DSM morphological matrix allows visualization of the damage propagation process in the transmission and provides an idea of the possible causes of transmission failure. The use of the proposed method is especially relevant to controversial cases. The original source of destruction and the scenario of subsequent failures has been established. Rational direction for improving the design has been found. Thank you for attention.
Dear colleagues, have a good day. The study Economic Justification of High Rotational Submersible Pumps Development for Water Supply Facilities is brought to your attention. Speaker Vladislav Kondus, Action Head of the Research Department of Sumy State University. The volume of energy consumption by pumping equipment is a critical aspect in various industries. It directly influences operational costs, efficiency, and environmental sustainability. Pumping equipment is commonly used in sectors such as water supply, wastewater treatment, oil and gas manufacturing, and heating, ventilation, and air conditioning. The energy consumption of pumping equipment is primarily influenced by several factors such as pump design, system characteristics, operational parameters, and the efficiency of the overall operation process. Pumps play a crucial role in transporting fluids from one location to another. The energy required for this task can represent a significant portion of the total energy consumption, up to 20% and more, in industrial and commercial settings. It's also important to correctly select the size of the pump according to the specific application requirement. Large pumps can lead to inefficient operation and unnecessarily energy consumption. Selecting pumps that meet system requirement ensures its optimal performance. Given the significant impact of pumping systems on energy consumption, ongoing research and innovation continues to explore new materials, designs, and technologies that can further improve the overall efficiency of pumping equipment. As industry strives for sustainability and reduced environmental impact, optimizing energy use in pumping operation remains a key area of effort. On the slide, you can see the aim and research tasks. The main aim of the research is to increase the market competitiveness of pumping equipment for the needs of the water supply sector by reducing its life cycle cost. Currently, in the field of pump construction, there is no single comprehensive approach to evaluating the efficiency of pumping equipment. The method of estimating the cost of pump life cycle, which takes into account the total cost of funds at each stage of its development, operating, and disposal, is considered the most complete. It should be noted that this approach doesn't take into account the influence of external factors, in particular changes in the cost of energy resources and services, inflation, cost, availability, and cost of materials, which can complicate such an assessment. Therefore, we developed test and improved the effectiveness of the systems of indicators of pump energy consumption and material capacity. It's easy to use. On the other hand, the proposed system allows for a quick and qualitative assessment of the life cycle cost of a large array of pump. In this research, this technique was used to assess the energy efficiency and material consumption of submersible pumps for water supply facilities. In the course of the research, we analyzed the cost of the main components of the life cycle cost structure for a line of pumps for water supply facilities. In particular, we analyzed the estimated energy consumption and energy intensity of more than 70 submersible pumps with casing pipe diameters of 12, 10, and 8 inches. Summary statistics by groups of pumps depending on the diameter of the casing pump and the calculating operating mode of QBAP are shown in the table. In the vast majority of cases, pumps with the same design but different number of stages were assigned to one group. The number of stages in the design of different groups pumps varied from 1 to 17 units. At the same time, it should be noted that it's impractical to modernize pumps with a small number of stages from 1 to 3 units by increasing the rotational frequency. This will lead to an increase in head and as a result the power consumed by the pump. The highest value of the energy consumption indicator according to the given method and therefore the highest electricity costs are observed in pumps of groups 6 and 7. These are pumps with the flow rate value of QBAP about 63 cubic meter per hour and the head in the range from 20 to 200 meters. These groups include 4 and 11 pumps respectively. Thus, in view of the data presented in the table, the most effective increase in the rotor frequency from 3000 rpm to 6000 rpm is seen in pumps of the fifth group. Thus, the ECV 1063-150 submersible pump with parameters and energy characteristics which are given in table was chosen as the primary pump for improvement. Based on the results of the research, a modernized design of the ZN 863-150 submersible pump with a rotor rotational frequency of 6000 rpm was developed. Thus, the energy consumption saving in the operation range from 0.6 to 1.2 of best efficiency point is from 1.6 to 4.8 kilowatts. For the operation mode of best efficiency point, taking into account the obtained saving results, 1.5 kilowatts, the saving on electricity were calculated when using the developed pump ZN in comparison with the indicators of the based pump ECB. The available Eurostat data were used as electricity tariffs. The obtained data prove significant cost saving when using the developed ZN pump in comparison with the indicators of the basic ECV pump for similar periods of time. The market value of the ECV pump as of August 2024 is about 64,000 Ukrainian hryvnias or about 1.5 thousand euros. Taking into account the weight of the pump, 200 kilograms, the cost of 1 kilogram of the manufactured pump is about 7.5 euros. The mass of developed ZN pump is about 50 kilograms, which is 4 times less than that of the existing ECV pump. This is achieved by increasing the rotational frequency of the pump rotor from 3000 rpm to 6000 rpm. Taking into account the experimental production, the cost of 1 kilogram of the manufacturing experimental pump, the ZN should be considered equal to 10 euros. Thus, its market value will be about 500 euros. Therefore, the market value of the ZN pump is about 1000 euro, or 67% lower than the market value of the ECV based pump. On the basis of the developed design of the pump as a finished technical solution, it's possible to further replace a number of operation pumps. Thus, the high unification level of development allows to replace 6 pumps of the current ECV pumps line by varying the number of stages. At the same time, the required head is created by changing the number of pump impellers in the range from 1 to 3 peaks. On this slide you can see the results of the study, which with your permission I will not read in order to save in time. The research was carried out within the framework of the National Research Fund of Ukraine project. The authors express their gratitude to the Sumy Machine Building Cluster of Power Equipment and the International Association for Technological Development and Innovation for supporting the research. Thank you for your attention.
Dear colleagues, my name is Vitaly Korenyi. I am from Lviv Polytechnic National University, Ukraine. I am glad to be here with you and to participate at the Grabchenkos International Conference on Advanced Manufacturing Processes InterPartner-2024. Today I want to present you the research results dedicated to the analysis of power consumption of a wheeled robot actuated by a centrifugal vibration exciter. Mobile robotics is a dynamically developing field that combines the elements of mechanical, electrical control and computer engineering to create machines capable of autonomous movement. Mobile robots come in various forms, from wheeled platforms and legged systems to aerial and underwater vehicles. Nowadays, specific attention is paid to vibration-driven systems, which represent a unique class of robots that rely on mechanical vibrations as a primary mean of locomotion. Vibratory robots typically utilize small vibration actuators and motors that induce mechanical vibrations. For example, unbalanced rotors, electromagnets, solenoids, dielectric elastomers, and other devices. The primary purpose of this study is to define the dynamic and force characteristics of a wheeled vibration-driven robot that is equipped with a centrifugal vibration exciter, designed in the form of an unbalanced rotor and with the overrunning clutches that provide one-way rotation of the robot's wheels. Herewith, the major attention is to be paid to establishing the relationships between the parameters of the platform's mechanical system and its dynamic and force characteristics at specific operational conditions. The primary scientific contribution of this paper consists in establishing these relationships between the parameters of the platform's mechanical system and its dynamic and force characteristics at specific operational conditions. The research methodology contains several main stages: developing the dynamic diagram of the robot's mechanical system and deriving the locomotion equations. Numerical modeling of the system's dynamic behavior in the Mathematica software under specific operational conditions. Creating the 3D design of the robot in the SolidWorks software. Constructing the laboratory prototype of the vibration-driven platform and carrying out the full-scale experimental investigations. The considered robot consists of 4 rubber wheels 1, which are in contact with the horizontal supporting surface. The front and rear wheels 1 are installed on the corresponding axis 2 with the help of the overrunning of free-wheel clutches and using the bushings bosses 4. The clutches 3 allow the unidirectional or single-way rotation of the wheels 1. Additionally, the ball bearings 5 are used to join the wheels 1 with the axis 2 and to hold the extra loading. In order to eliminate the wheels sliding along the axis 2, the clamps 6 are used. The axis 2 are fixed to the angles 8 of the robot's body with the help of the clamps 7. The DC electric motor 9 with the unbalanced rotor 10 is installed in the housing 11, which is fixed to the angles 8. The centrifugal forces generated due to the unbalanced masses rotation act through the motor 9 upon the housing 11 and cause the pushing effect on the robot's body. Let us consider the wheeled vibration-driven platform presented in this slide. On the platform's body 1, there is fixed the centrifugal vibration exciter or imbalance rotor 2. The platform unidirectionally moves along the supporting surface on the wheels 3, which are installed on the corresponding axis with the help of the overrunning clutches. The latter allows single-way rotation of the wheels, therefore the backward motion of the platform is restricted. Let us apply the XOY coordinate system related to the supporting surface. In this case, the generalized coordinate x1 describes the horizontal displacement of the platform. Another generalized coordinate phi defines the angular position of the imbalanced rotor with respect to the OX axis. The mass of the platform is denoted as M1 and the mass of the disturbing or imbalanced body is M2. The eccentricity of the vibration exciter is the distance LAB between the hinge A and the disturbing body 2. Neglecting the rolling friction of the wheels and considering the perfect surface or gripping capacity of the wheels, restricting their backward sliding, the following differential equation is deduced to describe the platform locomotion. In this equation, FBL is the so-called blocking force, which is generated due to the application of the overrunning clutches. The experimental equipment contains the voltage regulator 1, full-scale prototype of the wheeled platform 2, accelerometer 3, laptop 4, with motion software 5, digital oscilloscope 6, and Huntec software 7. The platform 2 is actuated by the centrifugal vibration exciter. The voltage regulator 1 is powered from the AC network of 230 volts and 50 Hz and provides the possibility of manual adjusting of the output direct voltage in the range of 0 to 24 volts. The specific voltage defines the rotational frequency or the angular speed of the vibration exciter. The sensor 3 measures the horizontal translational acceleration of the wheeled platform, and with the help of the USB Type-C cable transmits this data to the laptop 4, on which the corresponding whip motion software 5 is installed and allows for processing the experimental data. The oscilloscope 6 registers the voltage drop on the additional resistor connected in series to the vibration exciter. The obtained data are processed with the help of the Hunter software. The corresponding consumed current of the exciter's electric motor is defined based on the Ohm's law. In order to perform numerical modeling of the platform locomotion conditions, the direct differential equation was solved with the help of the explicit Runge-Kutta order 5 method, which is integrated into the Wolfram Mathematica software. The experimental studies, full-scale laboratory investigations of the wheeled platform locomotion conditions were conducted at the Department of Technical Mechanics and Engineering Graphics of Lviv Polytechnic National University. The simulation results show the time dependencies of the wheeled platform displacement, speed, acceleration and mechanical power at different angular velocities of the imbalanced rotor. The largest values of the mentioned quantities of respectively 0.043 meters, 0.086 meters per second, 6.8 meters per square second and 4.3 watts are observed at the largest angular speed of 157 radians per second or 1500 revolutes per minute. Considering the smallest rotational frequency of the imbalanced rotor of 52 radians per second or 500 revolutes per minute, the corresponding quantities take the following values: 0.0016 meters, 0.0032 meters per second, 0.084 meters per square second, and 1.44 watts. This allows for the conclusion that more energy-efficient regimes of the wheeled vibration-driven platform locomotion conditions take place at larger angular speeds of the imbalanced rotor. The experimental investigations showed that at the largest forced frequency of 1500 revolutes per minute, the current changes from 0.25 amperes to 0.35 amperes, while at 500 revolutes per minute, the narrowest spread of 0.29 to 0.31 amperes is observed. The average consumed current is about 0.3 amperes. The largest power consumption of about 7 watts is observed at the first frequency of 1500 revolutes per minute, while the smallest one of about 2.2 watts is reached at 500 revolutes per minute. Considering 3 investigated cases, the corresponding average values of the consumed power are the following: 6 watts, 4 watts and 2.2 watts. According to the experimental results, the highest acceleration values, ranging from 4.5 to 5 meters per square second, are observed at the maximum forced frequency of 1500 revolutes per minute. Consequently, the lowest values of these accelerations align with the minimum forced frequency of 500 revolutes per minute. Consequently, based on these experimental findings, the robot's average speed fluctuates from in the range of 0.0027 to 0.04 meters per second. Considering the time dependence of the wheeled robot displacement, its stepwise character is typical for all vibration-driven locomotion systems operating at stick-slip regimes. Unlike the systems in which the imbalanced body is rotating in the horizontal plane or whose exciters consist of two counter-rotating eccentric shafts, providing the constant direction of the excitation centrifugal force, the current experiments show that in particular operational conditions, the studied wheel platform can slide backward due to reduction of the friction forces between the wheels and spotting surface. In general, the studied wheel vibration-driven platforms can be connected in series by the controllable spring damping elements to form multimodal locomotion systems. This study delves into the overall design of a mobile platform featuring unidirectional rotating wheels propelled by a centrifugal vibration exciter. Roller-type overrunning clutches are employed for the installation of the robot's wheels. The centrifugal exciter is actuated by a DC motor, enabling convenient control of the forced frequency. The dynamic diagram of the robot's mechanical system is developed and the equations of its locomotion are derived. The numerical modeling of the system's dynamic behavior is conducted in the Mathematica software under specific operational conditions. The 3D model of the robot is designed in the SolidWorks software and the corresponding laboratory prototype is constructed and experimentally tested at the Bioengineering Laboratory of Lviv Polytechnic National University. The conducted investigations can be valuable for designers and researchers who work on the development and improvement of mobile vibration-driven robotic vehicles, capsule-type robots, pipeline cleaning systems, vessel inspection devices, etc. The completion of this research paper would not have been possible without the support of Alexander Kacher, Olena Lanitz, and Rostislav Redko, as well as all the staff of the Department of Technical Mechanics and Engineering Graphics of Lviv Polytechnic National University. Thank you for your attention and looking forward to cooperating with you.
Dear colleagues, your attention is presented with a report on the topic, Increasing the Service Life of the Pressure Block of the Planetary Hydraulic Motor. 1. Introduction and Major Challenges. Planetary hydraulic motors have high torque and low output shaft speed, which allows them to be used for direct, without gearbox, drive of various actuators. Therefore, they are used to drive active working parts of self-propelled vehicles and chassis systems. During the operation of planetary hydraulic machines, due to where the working surfaces of the rotors increase in the diametrical gap between them, the service life of the pressure block of the planetary hydraulic motor decreases. The magnitude of the diametrical gap, as a parameter that determines the service life of the pressure block, is initially, structurally, determined by the geometric error of the toothed surface of its outer rotor due to its manufacturing technology, design. Therefore, research aimed at structural changes in the rotors of the pressure unit in order to increase its service life at the design stages is an urgent task. 2. Aim and research tasks. To increase the service life of the pressure block of a planetary hydraulic motor by changing the design of its rotors, in order to ensure stability of the geometric and functional parameters of the pressure block, it is necessary to solve the following problems: justify the geometric parameters of the outer rotor, which determine the error in the location of its teeth, rollers. Depending on the design of the outer rotor, develop a mathematical apparatus that describes the relationship between the geometric and functional parameters of the elements of the pressure block, which determine its service life, carry out modeling of changes in geometric and functional parameters in the elements of the pressure block during operation for various rotor designs. 3. Research methodology. Studies of the kinematics of the movement of rotors during their contact interaction made it possible to formulate a design solution that reduces the error in the shape of the toothed surface of the outer rotor. The main distinguishing feature of the proposed design of the external rotor of the hydraulic machine is that it is formed by bodies of rotation housing one end teeth, rollers, rigidly, without gap, connected to each other. The proposed design of the modernized external rotor, due to the change in manufacturing technology, rotational bodies, ensures the error in the shape of the toothed profile within the range from 0.03 to 0.06 millimeters. Such an error in the manufacture of the toothed profile is sufficient to increase the service life of the pressure unit. Due to the error of the shape of the elements of the pressure block, there are radial and angular deviations, which characterize the position of the centers of the teeth of the internal and external rotors. Studies of the kinematics of rotor movement have established that the performance of the pressure block is determined by the ability of the internal and external rotors to self-compact when moving, ascent. An indicator of the ascent process is the rotation angle, which calculated for each contacting pair. The ability of the rotors of the hydraulic motor pressure block to self-seal, depending on location during ascent, is determined by the minimum value of the rotation angle in the contact pair. The developed mathematical apparatus that describes the relationship between the geometric and functional parameters of the rotors of the pressure unit allows, by modeling, to determine its service life, and therefore the hydraulic motor as a whole, even at the stage of hydraulic motor design. 4. Results. As established by kinematic studies, during the manufacture of pressure block rotors, its service life is significantly affected by the error in the shape of the mating toothed profile of these rotors. The presence of an error in the shape of the toothed surface of the rotors of a serial pressure block, due to the technology of its manufacture, causes a scatter in the maximum deviations of the positions of the centers of the teeth and, as a consequence, a dispersion of the gap in the area limited by curves 2 and 3. Research has established that the limiting state of a serial pressure block occurs at a critical value of the diametrical gap 0.12 mm, at which the ascent of the internal rotor no longer causes the process of self-sealing of the rotors. The change in the gaps between the contacting teeth of the rotors of a serial pressure block in the absence of a handicap error and a diametrical gap 0.12 mm displays curve 2. Similar studies were carried out for a hydraulic motor with a modernized pressure block. The dispersion of gaps in the area limited by curves 2 and 3 is caused by the presence of an error in the shape of the toothed surface of the rotors, the modernized pressure block, due to the technology of its manufacture. The limiting state of the modernized pressure block occurs at a critical value diametrical gap 0.37 mm, at which the ascent of the internal rotor no longer causes the process of self-sealing of the rotors. The change in the gaps between the contacting teeth of the rotors of the modernized pressure block in the absence of a handicap error and the diametrical gap 0.37 mm displays curve 2. Thus, it stated that by changing the design of the outer rotor, it was possible to reduce the error in the shape of its toothed surface and, as a result, increase, 3 times, the service life of the entire pressure unit. 5. Conclusions. The research has established that increasing the service life of the pressure block of a planetary hydraulic motor can be achieved by changing the design of its rotors, in particular the external rotor. Such design changes ensure stability of the geometric and functional parameters of the pressure block. The conducted studies confirm the theoretical premises described in previous of the authors of the influence of the diametrical gap and the error in the shape of the gear contour of the rotors on the change in the service life of the pressure block of a planetary hydraulic motor. Thank you very much for your attention.
Good day, dear participants. I'd like to present my report of a work, Optimal Geometrical Dimensions of Drainless Vortex Chamber Ejector of Homogeneous Medium. The reliability and longevity of blowers which have proven themselves when operating with homogeneous medium, are significantly reduced when pumping heterogeneous medium. Wear and reduction of efficiency of flowers with movable working bodies leads to the fact that it becomes expedient to use jets in many technological processes. However, jet direct flow ejectors, also having comparatively high efficiency reaching 30%, have significant longitudinal dimensions, which in some technological processes complicates their layout. On the other hand, the use of properties of swirling flows, such as pressure reduction on the axis, led to the creation of vortex ejectors, but their energy performance and efficiency were reduced. Thus, improving the energy performance of jet ejectors is an urgent problem. The solution to this problem can be the use of more perfect principles of energy transfer and technical solutions in the design of jet ejectors and pump based on the vortex chamber. Such superchargers are vortex chamber supercharger, which due to the use of centrifugal force have better energy efficiency in comparison with vortex ejector. The study consisted of 3 stages, and the aim of the study is to optimize the geometrical dimensions. In the first stage was experimental study of the vortex chamber ejector, and after that, in the second stage, mathematical modeling based on the solution of Reynolds averaged Navier-Stokes equation with the SST model of turbulence was carried out. After that, the experimental data were compared with the calculation results, and the conclusion about the adequacy of mathematical modeling was made. In the third stage, the planning of the numerical experiment was carried out, the factors and the target function ejector efficiency were selected. Vortex chamber ejector with two-sided suction of the pumped medium works as follows. Active flow creates a field of centrifugal force in the vortex chamber and corresponding pressure distribution along the radius. The presence of vacuum near the axis allows air to be drawn in through the 2 axial channels. The secondary flow acquires kinetic and potential energy through interaction with the flow rotating in the chamber. The mixed flow enters the tangential exit channel of the ejector, while there are similarities with the ejector in the process of transferring energy to the flow core through the turbulent exchange. The difference is the use of centrifugal force, which improves the performance of the supercharger by reducing the energy exchange losses between the carrier and the pumped medium. To achieve the set objectives, a special experimental setup was developed, as well as a transparent model of the ejector with a vortex chamber diameter of 50 mm was made. In the experiment, manometers were used to measure the pressure in all channels and the volumetric flow rate using Venturi tubes. Thus, the maximum pressure measurement error did not exceed 5 pascals. The formulas for calculation you can see at this slide, and thus the experimental performance curve of VCE of homogeneous medium with two-sided suction for geometrical dimensions, and all the dimensions are referred to the diameter of inlet suction channel. Diameter of vortex chamber was 7. Related height of vortex chamber was 2.8, and related diameter of supply channel was 0.85. Diameters of axial suction channels were 1.0. These geometrical parameters were chosen as initial parameters in the selection of experiment planning ranges. To simulate the flow of incompressible fluid, the OpenO-Form software was used to calculate the Reynolds equations. continuity equations, and SST model. OpenFOAM is a free and open source program that can be used to model almost all classes of flows, and this program often used to calculate violent flows and has been validated and verified for such problems. Figure shows the ejector characteristics modeled by numerical calculation and compare it with experimental data. Analysis of the characteristics shown in figure shows that numerical simulation can be used for further analysis and be the basis for the design of experiments to obtain the optimal geometric parameters and the maximum relative error in determining the flow rate, pressure, and efficiency does not exceed 4%. The adequacy of the characteristic points obtained by modeling was determined using F criterion, Fisher statistical criterion, and it was obtained that the model is adequate with a confidence level of 95%. A full free factor experiment was implemented to investigate the influence of the relative diameter of the vortex chamber, relative height, and relative diameter of the ejector supply channel. To evaluate the influence of the above factors and mathematical description, a first-order model was used. The values of the selected levels of varying factors are given in the table 1. Because small variations in flow rates and other integral performances were observed during the calculation with iterations, free values for iteration corresponding to maximum, minimum, and average flow rate. After calculating all the coefficients, equation that you can see at the slide for efficiency in % depending on factors encoded form takes the form that you can see. The statistical significance of coefficients was checked using the T criterion. The obtained equation was tested for adequacy. The hypothesis of the adequacy of equation was tested by F criterion. To bring equation to the form with natural values of factors, we use the coding formula and substituting natural values of factors into equation instead of codes 1, and you can see it in the slide. Reducing the relative diameter of the supply channel leads to an increase in efficiency, but at small values of the relative diameter and height of the chamber. The dependence of the ejector efficiency on the relative diameter of the supply channel is less apparent. The presence of maximum efficiency values in figure that you can see at the slide at the boundary of the variation area of the vortex chamber diameter and height indicates the possibility of further optimization of the ejector efficiency. Thus, design of experiment and obtaining the first-order regression equation allows us to confirm the hypothesis about the dependence of efficiency in all three studied factors. In this study, the regression equation described the changes in the efficiency of vortex chamber ejector depending on three factors was found. In contrast to the VCE with the drain channel, it was determined that the height of the vortex chamber has a significant role and significant effect on the ejector efficiency and should be minimized, which is caused by additional energy losses of the main flow due to increase in the area of contact with the walls and an increase in friction. In contrast to VCE with the drainage channel, in which there is an increase in efficiency with the growth of the relative diameter of the vortex chamber and the diameter of the supply channel. The opposite dependence is observed in VCE without a drainage channel. The presence of maximum efficiency values on the boundary of the variation area of variable values indicates the possibility of further optimization of the ejector efficiency, since the first-order regression equation given in the paper does not allow us to make an ambiguous conclusion about the presence of optimum. Thus, planning the experiment in obtaining the first-order regression equation allows us to confirm the hypothesis about the dependence of efficiency on all three studied factors, and it assumes the presence of optimum values near the variation boundaries. Further studies should be carried out to obtain more complex polynomial dependencies with increasing factors, variation areas, and maximum efficiency. So at this slide you can see the conclusions and optimization of geometrical dimensions of vortex chamber and supercharger channels for improving the energy characteristics of vortex chamber ejectors of homogeneous medium based on design of experiment methods is carried out. As the conclusions, I think that I will not read it out, and additional I want to add that along with linear effects, interaction effects were also significant, and it will be better to continue this research, and I hope that we will take a more optimal dimensions of the vortex chamber. Thank you very much for your attention. I hope that you will have questions for me, and I will be happy to answer all your questions about this work and this research. Thank you very much.
Good afternoon, dear conference participants. Your attention is presented on the topic Substantiation of the Spring Cam Retarder Brake Design Parameters Determination. An important element affecting the crane equipment safe operation, its durability and efficiency, is the crane's braking system that depends on the reliability of the braking device itself. The classic normally closed structural design of friction brakes during such brakes operation does involve significant dynamic loads in the drive and metal structures of the crane. This aspect requires additional attention when developing braking device in order to minimize dynamic impact on the crane, and thereby to ensure its operation, safety, and efficiency. The study purpose: implementation of a method to gradually increase the force acting on the friction pads in the retarder brake design using a cam mechanism for smooth braking of the machine. Research objectives: development of a design diagram of a spring cam retarder for the machine smooth braking. Determination of the main parameters of the spring cam retarder. In mechanical engineering and, in particular, in lifting machines, various design of pads brakes are used, which differ mainly in the schemes of lever systems. Usually, these brakes consist of levers and two external pads located diametrically with respect to the brake pulley. Braking of the mechanism by the brake pad occurs as a result of the creation of a friction force between the brake pulley connected to one of the mechanism's shafts and the brake pad connected by means of a lever system with fixed structural elements. Disc pad brakes have such significant advantages over the pad brake: better head dissipation, more significant braking moments, uniform pressure on pads, lower moment of inertia of the brake disc compared to the brake pulley, which improves the dynamic performance of the drive mechanism. The disadvantage of disc brakes which do not use vibrational devices is that when the brake pads are instantly pressed against the brake pulley, large dynamic loads occur in the mechanism's braking systems. Taking into account the advantages of cam mechanisms, proposed is the design structure of a spring cam retarded brake shown in Figure 1. In the body 1 of the retarder brake, two diametrically opposite cavities, A and B, are arranged, and each of them contains a twisted or disc spring 2. A piston 3 with a rod and a nut 4 screwed at that rod end. Pads 5 are pivotally attached to the piston, and a cam eccentric shaft 6 is installed in the body. Braking of the machine mechanism with a spring cam retarder brake occurs due to the creation of a friction force F between the cam 6 connected to one of the mechanism shafts and two brake pads 5, which both are pressed against the cam due to the normal force P created by compression of the spring 2 as a result of the corresponding movement H performed by the piston 3 when the cam rotates. In this case, the maximum displacement of H occurs twice in one revolution of the cam. The maximum displacement of H at a given eccentricity E will be equal to Formula 1. Then, taking into account the stiffness of the spring C, the maximum normal force P is found as Formula 2. The value of the radius of the application of the friction force will have the form Formula 3. With respect to the above, the braking torque of the spring cam retarder brake will be equal to Formula 5. The normal force P depends on the spring stiffness and the displacement H. With a gradual increase in displacement value H, respectively, also gradually increases the normal force P. Figure 3. Thus, smooth braking of the machine is ensured during operation of the spring cam retarder brake. There exist conflicting requirements for pad and disc pad normally closed brakes. On the one hand, it is necessary to ensure the repeat closure and opening of these brakes, and this causes large dynamic loads in the machine metal structure and drive. On the other hand, to reduce dynamic loads, the use of complex structures of electromechanical pushrods, electrohydraulic forces is required, which significantly increases the cost of such brakes. Therefore, it is advisable to use two brakes at such machines. The brake whose design scheme is proposed in this paper can fulfill the function of a retarder, and the design of such a retarder is much simpler and more compact. In the event when is necessary to significantly increase the braking torque, possible is to use the multi-threading principle, namely to place several. For the example, 3 spring cam mechanisms on the shaft. Figure 4. Add that in order to evenly distribute the loads on the retarder brake shaft, each of the spring cam mechanisms 1, 2, 3 shall be offset relative to each other by the required angle. Thus, the braking torque will be increased 3 times. Proposed is the design scheme of the spring cam retarder brake, which ensures smooth braking of the machine, while the brake design can be simple and compact. Analytical dependencies have been found to determine the spring cam retarder brake main parameters. It is proposed to use the multi-threading principle to create design of spring cam brakes with a high braking torque. It is planned to produce an experimental sample of the spring cam retarder, to develop a stand for the study of experimental samples, and to give recommendations and the design of the spring cam retarder. Thank you for your attention.
Do you hear me?
Yes.
Okay, thank you, my dears. Thank you. Sorry, I closed my YouTube channel because I heard two voices. Excuse me. Thank you for all the participants, for all the presenters on our session 1 on the subject design engineering. From my point of view, everyone was interesting, but every has a little bit another point of view for the devices, for the equipment, for your solutions, and every concern to the modeling, tools in the modeling, how to optimize the construction, the design, the device, etc. At this moment, I look to the chat. Have we any questions to our presenters?
Dear colleagues, I'm sorry, we have a question from the conference hall. So if you are ready, we...
Yes, maybe in the what was the presentation, I start for the first, okay?
Okay.
The first presentation was the heuristic analysis of the accident of the ship Radler propeller columns, and it was the case study. The presenter was the Victor Ivanov. Victor is with us. Victor Ivanov, I look on the Victor.
Yes, Professor Ivanov is online.
Yes, is with us. Of course. Any questions to this presentation from the audience? No, everything was clear, probably, but from I prepare one question. Why did you choose the heuristic method to collect the information from another dangerous situations in this device, in the ship? Okay? Because in this world, in now times, we have a lot of another new methods, especially artificial intelligence, etc., etc. Why the heuristic method did you use?
Why the heuristic methods? I propose a new heuristic method. The methods that we, I think, know the DSC, Design Structure Matrix.
Okay.
And another method that you know, I think, the morphological matrix or morphological map. I proposed to edit one matrix to another, to show not only the interrelation between elements, but show the damage of elements, the degree of damage of the elements. In this way, you have more visualization process of damage progress in the machine.
Okay. That was important. The damage progress we can see in your matrix or those. And from my point of view, the heuristic method, especially in the matrix view, is easy to use and visualize the process. As in this case, the damage process. Okay. Did you agree with me?
Yes, of course, degree.
Okay, fine. Thank you. Maybe another questions from the audience?
Thank you for you.
No questions. Thank you very much.
Okay, everything was clear. That goes to the our next presentation. It was the subject in the economic justification of high rational submersible pumps developed for water supply facilities. It was presenter was the Professor Władysław Kondus. Władysław is present. I look.
Yes, I'm here.
Okay, thank you. Hello. The questions to the professor, to the presenter Władysław Kondus from the audience. I don't hear, but maybe everything was clear. But maybe not so clear for me. It's a joke. But one question: your new proposition of the pump was tested in the real conditions?
Yes, we tested it in real condition. Also, we tested it according to numerical investigation due to NCCFX software.
Okay, thank you. And one more. In the calculation sheet, I see you take the less information about the maintenance of the new kind of pump. From this point of view, how long you tested the new version of the pump? 30 years? 10 years?
We tested our pump
5 years? 3 months?
It was about five tests on the real condition on the.
But what was the period?
It was about 3 or 4 hours.
But you, in the calculation sheet, prepare the maintenance service cost to less.
It's
depends to the previous version on the pump. That's a very question mark in this point.
We tested first of all, we tested the efficiency indicators on the test branch, but the maintenance is calculated numbers.
Okay, I agree with you, but I see the lower cost of the maintenance in the period of 10 or 30 years, which you present in the sheet table. Maybe another prognostic method or something like this. That's my suggestion, of course.
Yes, it's prognostic.
Thank you. But another questions from the audience? Please, we have time. No questions? Oh, let's go to the next presentation. That was once more. Okay, analysis of the power consumption of the wheeled robot actuated by the centrifugal vibration exciter. That was very interesting design or the rather construction of the robot. Of the especially in the motion and other parameters, how mechanical parameters. But the questions to presenter to Professor Vitaly Korendli.
Yes, to this presentation we have a question from the conference hall. So I give a chair to my colleague.
Okay, please.
My name is Larshin Vasil Petrovich, professor. I'm working in Odessa Military Academy. I should like ask as for this presentation. The first, what is the type of engine that is electrical or internal ignition? Please. What is the type of engines in your wheeled platform?
Thank you for the questions, and I redirect the questions to the presenter, to the Professor Vitaly. Please, if you can answer, that the stand is yours.
It was my first question.
Okay, we will wait for Vitaly. Vitaly is present. I look on the list. I didn't see. No, I see him.
He is absent.
I see on the panel, but we didn't hear any voices or the others.
Maybe we can switch to another presentation and come back to Vitaly
Okay.
later. Maybe it's technical problems.
Maybe technical problem. And in this moment, we go to the next presentation, increasing the surface life of the pressure block of the planetary hydraulic motor. It was a lot of researchers how to improve the service life of the pressure block in the planetary hydraulic motor. The paper was presented by Anatoly Panchenko. The questions to this presentation, please.
There is no questions and
no questions from the audience. Yes.
And I
yes,
don't see the speakers from this presentation in the chat.
Okay, that's
so we can announce questions for them, and maybe they will receive it later.
Okay, of course I prepare one question, but if they are absent, we go to the next. Okay, the next was optimal geometrical dimensions of dryness vortex chamber ejector of homogeneous medium. This paper optimized the geometrical dimensions of the vortex chamber and supply channels to improve the energy performance of homogeneous medium vortex chamber ejector based on design experiment methods. And of course, after the experimental studies, the new project, the new design was prepared. Questions to the Andriy from the audience, from the hall?
The same situation. No.
Same situation. Sorry. I sure the presentation was clear, and next, the last, we heard substation of the spring cam rotating brake design and its main parameters determination. The article was presented by Władimir Semeniuk, and of course that's the time for the questions to this.
One question, if possible.
Of course, it's possible. The voice is the whole, please.
Have you taken into account the uneven distribution of the load between parallel brakes?
Okay.
Unfortunately, speaker is not here. But thanks to the online presentation, we can send this question to the authors. We are so sorry, but the situation now is very difficult in Ukraine, and sometimes it is unpredictable. So no speaker at this moment.
I understand the situations, but from this point of view, I write on the chat, please write the questions, and from this point of view, the question can be sent to the authors. Yes, it will be a little bit easier. Or, of course, you can directly send the questions to the authors of each of the presented articles. And at this moment, Vitaly is present from the one of our presentation with concern to the robot, the special construction of the robot. I look on the. He's on the list.
He's on the list, but
he's absent at this moment. Only a ghost. Something like this. No, any response from his side?
Okay, thank you very much,
Thank
Professor
you
Olaf
very
Fischer.
much, all the participants. Thank you, Vitaly, for the invitation. Thank you, and I wish you, of course, a lot of good situations and good health in Odessa, of course, in the internet at this moment online. Thank you for the communication. Thank you for all of you. All the best for us, for you, of course.
Thank you very much for your time. Thank you very much for your knowledge and expertise.
No problem.
It is important for our participants. And dear participants, next session will start according to the schedule at 3 p.m. So please stay with us during the next session. Now is a technical break.
My name is Larshin Vasily Petrovich, professor. I am working in Odessa Military Academy, Ukraine, and Odessa Polytechnic National University, Ukraine. Now we are beginning the next session, session 2. We have 6 presentations, namely, the first presentation, modeling the dynamics of centerless mortise grinding on rigid supports by Vasil Chaly, Sergei Moroz, Anatoly Tkachuk, Valentin Zablotsky, and Oleg Zabolotny. Second presentation, increasing the continuous operation time of the diamond cutting disc when using various cooling media by Tatiana Chumachenko, Alla Bespalova, Olga Dashkovska, Alexei Knush, and Tatiana Nikolaeva. Presentation number 3. Development of a simulator program for studying the effect of cutting modes and cutting temperature by Vladimir Gugnin, Lyudmila Perperi, Gennady Borsky, Ganna Goloborodko, and Vladimir Goloborodko. Number 4. COCOSA method-based evaluation on cutting parameters in turning of AISI 1040 steel, underplane, and nano molybden S2 reinforced cutting fluid assisted MQL methods by Yusuf Gyonay, Yusuf Furkan, Yapen, Ruslan Jemaladinov, Esred Jemilov, and Alpa Yusal. It was presentation number 4. Number 5. Modeling and optimization of the process of drilling holes in carbon fiber reinforced polymer parts by Alexander Motoshin, Sergei Vislov, Viktor Antonyuk, and Oksana Voloshko. And the last presentation, a method for determining the forces and coefficient of friction on the back surface of cutting tools and their dependence on processing conditions by Mykola Mazur and Volodymyr Milko. So let's start the working. The first presentation is modeling the dynamics of centerless mortise grinding on rigid supports by Vasil Chaly, Sergei Moroz, Anatoly Tkachuk, Valentin Zablotsky, and Oleg Zabolotny. So,
Vasil Petrovich, at this moment we need a slight technical break due to technical reason. 2-3 minutes and we will start video presentations. Sorry for interrupting you.
Hello everyone. I am glad to present to you the work with title Modeling and Dynamics of the Centralized Mortise Running of Beach Supports, which was done by me and together with my colleagues. Sergei Moroz, Anatoly Tkachuk, Valentin Zablotsky, and Oleg Zabulotny from Rusk National Technical University. As you know, that bearings are an important part of many mechanisms and machines. The modern level of development of bearing production necessitates the creation and implementation of technological process, the application of which provides the necessary indicators of the operational properties of roller bearing parts. So the purpose of the research which was done is to develop a complex mathematical model of the Swaggle 50 running machine, which uses centralized motorized running process to analyze the influence of the dynamic parameters of the machine and the geometry of the adjustments of rigid support on the formation of the waviness of the detailed surfaces. So, to reach this purpose, we use the methodology and try to describe the machine with mathematical model. Running machines are made up of individual components, including motors, feed machines, bearings, running wheel, etc. So, for each of these components, resonates at one or more separate frequencies. Machine components are solid structures that can be modulated as a discrete set of individual elements consisting of linear springs, mass, and dampers. Use the logic thinking. We describe the running machine and separate of different parts. We also present the MTP system of the motorized centralized running machine, for example, the Swaggle 50 model, which are usual running machine for bearing production, and in the form of a linear mechanical model, and consider elastic moving the OX axis. In expression 10, which you can see below, a system of linear inhomologation differential equations of the second order is obtained. We describe the movement of the elements of the MTP system of the Swaggle 50 machine. After substituting the accepted assumption in the equations of system and transformations, we get more easier from the previous formulas. After that, to find the roots, the characteristics equation should be solved. And we take for that the next initial conditions. After transformation, the system 10 with initial conditions using direct and inverse Laplace transformation. After carrying out a series of manipulations, the vibration displaced of the center of the part along the x1 coordinate was obtained in the form. Expression of the vibration displacement of the remaining elements 2, 3 and 4 of the MTP system are similarly found. You can see this below in the formula. Then, after do the theoretical investigation, was done practical measurement of frequency of each part of machine. Here you can see the results of these practical measurements. Also here you can see the diagrams which was done during this measurement of practice of each part of machine. After that we got two diagrams. Figure 3, you can see the frequency response equation of the machine based on vibration parameters, which was done during practical measurement. And the figure 4, you can see the frequency response gets from mathematical model. And if we compare them, they are very close, very similar. What can give out for us conclusion that the mathematical model is good. After that was done the combined condition with machine. Here you can see analyzing of the depends of the dynamic stability of the machine on the geometry of the adjustment of the reed supports. It means we combine together characteristics of machine and characteristics of sets the reed supports. Here in the diagram you can see the lines which we get from the machine after mathematical modeling, and also the line which we get after mathematical modeling the setting of the reeds supports. And here you can see that's very dangerous is point where these both two diagrams are crossed. And we can see the frequency machine and growth rate is very high. This point is very dangerous for this machine. After that was create the diagrams where we put the points which are dangerous for the setting of the reed supports. Also here you can see the angles Phi1 and Phi2 and which condition for vibration they together do. Based on that, later we will use the best condition for setting of the reed supports. Exactly on this diagram, the main trends of dynamic stability during centralized mortgage running of the reed supports area is present, and the dark place are more worse, and place or areas which are white are better for the running machine. For conclusions, based on the conducted experiments of the MTP systems of the Swaggle 50 gun machine and the mathematical model and dynamics diagram, we was proved that the vibration of the machine affects the final accuracy of the manufactured part is 3 ways.
Dear participant, our team of authors present an article called Increasing the Conditions Operation Time of the Diamond Cutter Disk Then Using Various Common Media. When processing natural and artificial building materials, it is important to obtain precise cuts and perfect edges, especially when processing ceramic products. A diamond cutting disk of the material base can do this job during high-speed cutting and grinding. A large amount of heat is generated, and the disk heat up to 650 degrees Celsius and higher. At such temperatures, graphitization of diamond grain occurs, and as a natural result, cutting stops. In addition, the diamond blade becomes deformed, causing it to jam in the workpiece. Cooling of the cutting disc can be partially as a compilation by blowing a boundary wire of air. However, this is ineffective for significantly reducing the temperature of the wheel and increasing time of continuous operation on the cutting disc. Reducing the temperature of the cutting disc is possible by replacing the air boundary wire with another type of cooling medium. The possibilities of replacing the air boundary wire with another type of cooling medium. This measures also to increase the time of continuous operation of the disc. At present, there is no database on the purpose of cutting mods. The synthetic diamond disk each will determine the patterns of heating and cooling of the diamond cutting disk during operation. There is no method for determining the time of operation up to the critical temperature, and the issue of increasing the resource of the time of operation up to the critical temperature hasn't been considered. Fork carried out mathematical modeling of the operation of the diamond disk in order to study the heat exchange occurring between the rotating disk and the boundary wire of air. The fork examined various cooling media and various devices in order to increase the safe operation time of cutting disk. Research methodology. The research methodology involved measuring the disk temperature after 1 minute of operation. The disk was stopped in a stationary state due to a special operating circuit, and immediately after stopping, the temperature was measured by a temperature sensor, which was specially designed and manufactured for the purpose. You can see it in the figure 1. The temperature sensor consists of two semi-cylindrical holes, first made of steel 45, within which, through insulation-free, a thermal electrode 4, made of annealed chromo with a diameter of 0.2 millimeters in clamped. The cold end of which is led to a recording device in a millivoltmeter. To the close the electrical circuit, the second terminal of the recording device is connected to the sensor body, thus forming a thermocouple chromal steel. The end phase of the temperature sensor is ground this diamond disk to a roughness of Ra 0.16. Then grinding, the sensor body and the thermoelectrode are connected as a result of metal sheeting. The DC amplifier is used to amplify the signal. To measure the temperature, then grinding a specific part, they use temperature sensor built into the wheel. The temperature sensor consists of two copper-contained flow plates, between which a gasket made of non-conductive material is placed. The use of these thermocouples make it possible to obtain visual thermal pulses and to evaluate from them the relationship between the contact temperature, instantaneous temperature, and post-grinding temperature. The wheel temperature was measured then cutting without cooling, then cutting with air cooling at a temperature of -50% Celsius per Celsius using a Rankine H tube, which you can see in figure 3. Then cooling with fog due to fine extractor spray and water, then cooling with 5% natrium hydrocarbonates solution of the water. Then measuring the temperature when cutting this circle without cooling. The process continues for a minute, after which the circle was electrically breaking, and the temperature sensor touched its side surface. The cooling of the cutting disc is a finely sprayed cooling medium using an ejector tube is shown in the figure 4. Determining the surface temperature of the cutting disc is the case of contact heat exchange between two solid bodies under boundary condition of the fourth kind you can see in the figure 4. After this, we have boundary condition in the equation 2. After this, the solving the task using the Laplace transform in the equation 3, and we taking the temperature of the circle as T2 and somewhat simplifying the solution, we obtain the equation number 4. The mathematical modeling is confirmed by the result of the study of changes in the temperature of the cutting disk dependent on operation models you can see in figure 5. Curve 1 shows the time of heating the disk to critical temperature when cutting depending on the value of the vertical feed. This time sharply decreases with increasing vertical feed. Curve 2 shows the time of heating the disk to the critical temperature depending on the value of the vertical feed, then cooled by airflow of negative temperature. Curve 3 reflects the time of heating the disk to the critical temperature, then changing the value of the vertical feed, then cooling finally dispersed Cm. Curve 4 shown the time of heating the disk to the critical temperature when 5% aqueous solution of natrium hydrocarbonate is supplied as a cooling medium. Then heat transfer in a disk with a water-based coolant must be taken into account. The two types of heat transfer are possible here. First, heat exchange to the disk with the Cm, then the temperature of disk is slightly lower than 100 degrees Celsius. In this case, the convective process of heat transfer is carried out according to this thin fluid flow around a fluid plate. Heat exchange of the disk heated above 100 degrees Celsius. In this case, the water falling over the surface of the disk boils, and 3 cases of cooling as possible. Cooling through a vapor film, cooling this nucleate boiling water, and cooling this mixed character of boiling. Vapor film is formed, then it breaks off, nucleate boiling set in, and then the process is repeated. In this slide, we can see description of the heat transfer for the different type of heat exchange shown in the slide 4. You can see this in formulas 5 to 9. Disk cooling after cutting. The description of the operation cycles of the cutting disk will be incomplete in the cooling time of the disk to the ambient temperature is not taken into account. Boundary value task of the thermal conductivity in the polar coordinate system has form in the which we can see in the equation number 10. Initial conditions in the equation 11 and boundary condition in the equation 12. After this, we have a 2D finite element mesh. It's in the figure 6. Equation 10 with the indicated initial and boundary condition is solved by the finite difference method by FMLab, program of ComSolve company. The solution of the case of air cooling is shown in the figure 7. The solution for the case of cooling of the OS under pressure based on water. This water have 5% of natrium hydrocarbonate solution. It is shown in the figure 8. The conducive research made it possible to develop cutting modes that allow to increase the efficiency of technology of cutting stone building materials. You can see this in the table. And let's make conclusions. The working cycle cutting plus cooling will be as follows: cycle cutting using a round Hirsch tube and cooling the inhibited disk by cooling medium irrigation. Cutting time 26.6 minutes, cooling time 1.4 minutes. Total 28 minutes. Cutting this disk while cooling the working zone of the cooling medium under pressure and cooling the inhibited circle by watering the cooling medium. Cutting time 33.3 minutes, cooling time 1.4 minutes, total 34.7 minutes. The productivity of this working cycle is 20% higher. It can be concluded that if you can be satisfied with a moderate work performance, Is it more adventurous to use coolant with a round-carriage tube, since it is much easier? When cooling the disk with a jet or water-based cooling medium, its supply speed must be high enough so that the flow around the disk occurs in the turbulent mode, which allows you to obtain a nuclear boiling mode and significantly increase the operation time of the cutting disk in the continuous mode. Working this flow states allow you to increase the operation time of cutting disk, which significantly increases safety, increases productivity, and saves resources. After finishing the cutting work, the circle should be cooled by water in the water-based cooling medium. This makes it possible to roughly reduce the disk cooling time and obtain the efficient cutting plus disk cooling work cycle. Thank you for your attention.
Hello my dear colleagues. Before starting the report, let me introduce myself. My name is Vladimir Golobrodko. I am a third-year postgraduate student in the Metrology and Measurement Technologies program at Odessa Polytechnic University. The presented article was co-authored with Volodymyr Gugnin, Lyudmila Perpery, Gennady Oborsky, Ganna Golobrodko. Subject of my report is development of a simulator program for studying the effect of cutting moles on cutting temperature. Today, the study of temperature that occurs in the cutting zone is still a relevant issue. These processes are expensive due to using materials, metal cutting tools, technological equipment, and the expenditure of energy for mechanical processing. Nowadays, many studies have been conducted that emphasize the importance of using industry technologies for sustainable development in various industries. It is also important to understand that the trends of industry are aimed to combining production with digital technologies, for example. When applying software for modeling and optimizing technological processes, speeding up development and bringing products to the market. Therefore, part of research equations, especially at the prediction stage, can be solved with the help of computer modeling with using of modern software products, which will also partially solve the issue of saving resources and reducing the impact on the environment. The purpose of the thematic study is to create a program for automatization of the process of calculating the cutting temperature and visualization of the obtained results in the form of two-dimensional and three-dimensional graph of the dependence of the cutting temperature on the cutting technological parameters and the ratio of the processing material-tool-material pair. The aim of research tasks. The aim of this thematic study is to develop a program for automating the processing of measurement results and their visualization in the form of two- and three-dimensional graph. This graphical visualization provides an opportunity to estimate the possible range of temperatures occurring in the cutting processes for different pairs of materials and variable amounts of feed and cutting velocity. Research tasks. To describe the process using mathematical modeling. To make a software implementation of the process. To test the virtual instrument and analyze the obtained result. Research methodology. During development of the simulator program for automated calculation of the cutting temperature with using Skylab software, it was used based on the principle of measurement by the nature thermocouple method simulation. The scheme of the experimental equipment is shown in Figure 1. You can see it on the picture. The processed workpiece is clamped in the chuck jaws of the cartridge and it pressed by the center of the rear tailstock. To minimize the number of extra thermocouples that arise at the junction of the workpiece machine, the last one is desirable to isolate from both the cams of the chuck and from the rear tailstock. Tool also should be isolated from the tool holder by insulations. Multi-voltmeter is connected from one side with a carbide cutting insert and by the wire with a mercury slip ring. In the process of cutting at the point of contact of different materials due to heating, the thermoelectromotive force arises, which is resolved by a multi-voltmeter. Before starting the measurement, the multi-voltmeter must be calibrated in Celsius degrees to convert the received data into temperature. This is critical to obtaining accurate temperatures. The obtained experimental data were processed according to the method of multi-factor planning of the experiment, and the dependence of the cutting temperature on the cutting modes was obtained. These dependencies were taken as mathematical models for the development of the program simulator. As example for this article was chosen for different pairs of materials: processing material, tool material, carbon construction steel, tungsten, titanium, cobalt alloy, gray cast iron, tungsten, cobalt alloy, alloy structure steel, tungsten, titanium, cobalt alloy, titanium alloy, tungsten, cobalt alloy. The choice of material for specified pairs is related to the most common application in industry. Labeling of processed materials indicated in the program is accordance with EN standards and tool materials. In accordance with standard ISO 513/2012. The input parameters for automated calculations of the cutting temperature are the number of revolutions of the workpiece per minute, the feet of the tool in millimeters per revolution of the part, the depth of cut in millimeters, the diameter of the part in millimeters, and the type of material of the part by figure 2. All parameters can be varied in different combinations before the start of the calculation. For the calculation of the confidence interval of the temperature measurement result, the user needs to set the confidence probability value. For calculating of the cutting temperature, the user needs to press the button Calculate. After calculating the cutting temperature, its numerical value T and the value of the confidence interval epsilon are displayed at the bottom of the program window, and the graph of temperature change during the cutting processes appears in the separate window that you can see on figure 3 of the virtual oscilloscope. There are a number of measurement results were processed in the following sequence. The probable value of the cutting temperature measurement result is the arithmetical mean value of the sample, the value of which can be determined by the following formula number 5. The root mean square deviation, capital letter S, sub 0 from the mean value was calculated according to the formula number 6. The confidence interval epsilon of the random error of the measurement result was determined by the formula number 7, where T sub C is a student's distributional coefficient. Result and discussion. By program, you can analyze the dependence of the cutting temperature when varying the parameters of the cutting velocity and fit at a given value of the cutting depth using a graphic visualization of the three-dimensional dependence of the cutting temperature in the cutting and feeding speeds. For example, at figure 4, there are shown three-dimensional graphs of the surface, which shows the influence of variable technological cutting parameters, fit rate f in the range 0.1 to 3.0 mm per revolution, cutting velocity v in the range of 0.1 to 3.0 meter per second, and value of cutting depth t, which is 4 mm, as constant for different pairs of processing material to material. For visualization of the results of the program in the article are presented commonly used materials in the field of mechanical engineering and the typical range of cutting modes for their processing. The described ranges of technological cutting parameters are shown as an example. However, it should be noted that by this program it is possible to obtain cutting temperature values for different range of cutting regimes and various material pairs. When performing temperature analysis by engineering or research, this graphical visualization provides an opportunity to estimate the possible range of temperatures occurring in the cutting process for different pairs of material and variable amounts of feed and cutting velocity. As it is known, the cutting temperature significantly affects the wear of the cutting part of the tool and the quality of the machine surface. So understanding the possible temperature ranges under different machining conditions is important. As can be seen from the graphs at figure 4, for the specified pairs of materials, the temperature is higher when working with higher cut velocity and feeds, and also that by varying the parameters of the feed and cut velocity, the desired temperature range can be reached, which are able to ensure the operation of the tool in a normal state and the required parameters of the quality of the processed surface. However, it's uncomfortable to use three-dimensional graphs to detail the effect of one or another technological parameter. That's why the possibility to use two-dimensional graphs was added, which would allow researchers to determine which of parameters has the pre-dimensional, more significant or bigger influence. As the detail the obtained parameter values on two-dimensional graphs, this program allows change zoom in the graphical window to give the opportunity for a more thorough analysis of the obtained dependencies in the graphical form. The screen shows graph of the dependence of cutting temperature on processing models for such material of parts: carbon construction steel, tungsten, titanium, cobalt alloy, and gray cast iron, tungsten, cobalt alloy. This screen shows graphs of the dependence of cutting temperature on processing models for such materials of parts: alloy, structural steel, tungsten, titanium, cobalt alloy. In order to validate the suitability of the simulator calculations of cutting temperature, were performed using formulas from 1 to 4 for the processing conditions which are listed in table. The relative errors of the simulated temperatures, capital T sub s, compared to the temperatures capital T, which are calculated by formulas from 1 to 4, are in the range from minus 0.4% to plus 3%. This range of errors is acceptable for studying the influence of processing conditions on cutting temperature under industrial conditions. This table presents the compression results for increased cutting conditions. In this case, the relative errors are in the range from minus 0.01% to plus 4.7%. This range of errors is also acceptable. Conclusions. The program proposed in the case study was created using the Skylab software environment, which an open source license, which allows you to calculate the value of the cutting temperature for each pair of processing material tool material. The result of the program's work is the construction of three-dimensional and two-dimensional graphs, which allow to study the influence of processing modes on the cutting temperature depending on the variation of various processing conditions. The program also generates an oscillogram of temperature change during cutting, which is displayed in an additional window. It also should be noted that conducting experiments by researchers is often accompanied by significant financial costs, such as the cost of materials, tools, and energy costs for equipment operations, and is time-consuming. Therefore, according to the authors, it is appropriate to use the PROCEED program to identify the influence of parameters of cutting modes and other conditions processing to the cutting temperature at the preliminary stage, at the stage of forecasting, before conducting physical experiments for the implementation of tasks of integration of digital technologies in manufacturing within the framework of the concept of Industry 4.0. This program can be used during the stage of modeling and optimization of technological processes to accelerate the release of high-quality products to the market. The proposed program can also be used as a computer simulator, which allows you to simulate various conditions of the cutting processes when studying the influence of technological parameters on the cutting temperature, which makes it possible to use in the educational process, including the use of remote technologies. Thanks for your attention.
Welcome to all dear participants. I'm Yusuf Furkan Yapan from Yıldız Technical University. I would like to present our work on the titled COCOSO method-based evaluation of cutting parameters in turning of AC1040 steel under plain and nano molybdenum disulfide reinforced cutting fluid assisted MQL methods. In the machining process, it is desired to minimize cutting force, surface roughness, and cutting temperatures. In dry machining, high cutting force causes the cutting zone to reach high temperature. A high local cutting temperature affects the surface and surface properties negatively. Although wet cutting is seen as the solution to this situation, it causes problems in terms of sustainability. For this reason, recently, the minimum quantity lubrication, that is MQL method, has become popular with vegetable-based cutting fluid, which is known to be environmentally friendly. However, since the vegetable cutting fluid has a low cooling lubricating capacity. Its performance should be increased by adding nanoparticles. Scholars have been very interested in the MQL method with the nanofluid for a few years due to superior cutting performance and contribution to sustainability. Still, this is an area that needs the more study and attention because different kinds of nanoparticles and cutting oils have different effects on the different kinds of materials. This study aimed to evaluate the machining performance in terms of resultant force, cutting temperature, surface roughness, and material removal rate, obtained by using 3 different cutting speeds and 3 different feed values in turning of AC 1040 steel, under MQL with vegetable cutting oil and NMQL with nanomolybdenum disulfide added nanofluid. Then the appropriate process parameters were listed and selected in the applying the combined compromise solution, that is, COCOSO method. The methodology of the presented study consists of 2 parts, the experimental section and the multi-criteria decision-making section. For resultant force, cutting temperature, surface roughness, and material removal rate measurements, the experimental setup and experimental details are given in figure and table respectively. As can be seen from the table, a fixed cutting depth and cutting length were used to each experiment. Different cutting speeds and feed values were used under the MQL with vegetable cutting fluid and MQL with 2.5% by weight molybdenum disulfide nanofluid methods. In the preparation of nanofluids, nanoparticles were first dried in the oven. Then nanoparticles were added to the cutting fluid at the determined weight ratio. In addition, a lecithin emulsifier twice the weight of nanoparticle was added to the cutting fluid to extend the precipitation time of nanoparticles. Finally, the fluid was mixed with the digital homogenizer. Kistler brand 9257BA model dynamometer measures the cutting force, feed force, and radial force, and the resultant force is calculated in the presented study. The tool holder, which allows the connection to specially designed thermocouple to measure the cutting temperature, is connected to the dynamometer. The tip of the thermocouple is in the contact with the underside of the cutting edge region of the uncoated carbide insert. Surface roughness values were measured using the Mitutoyo surf test device. Material removal rate values were obtained by multiplying the cutting speed, feed, and depth of cut. Combined compromise solution method, in short COCOSO method, was first established in 2019 by Yazdani et al. The aim of the COCOSO method select and rank the alternatives with respect to decision variables. The method has 6 steps, and these are constructing the decision matrix, calculate the normalized decision matrix, total of the weighted comparability sequence, all of the power weight of comparability sequence, relative weights of the alternatives, ranking of alternatives. In this section, firstly the results of the resultant force, cutting temperature, surface roughness, and material removal rate are given. Then the alternatives ranked and selected by COCOSO are given. Experimental results for resultant force and cutting temperature are given in figure. Increasing cutting speed and feed increase the strain rate in the material, and the increase in strain rate causes the hardening of the material, because it doesn't allow the time for the dislocations to move in the plastic deformation of the material during the cutting process. This situation resulted in the increase in cutting force. The results obtained in terms of the cutting temperature show that the increasing the feed value increased the cutting temperature in the 2 cutting condition. In the MQL method, where the effect of the cutting speed is also included, the increase in the cutting speed increased the cutting temperature. However, in the NMQL method, due to the high cooling performance and the decrease in cutting time, the cutting zone couldn't be heated, and a decrease in cutting temperature occurred with the increase in the cutting speed and increasing cutting time. When the effect of the cutting environment on the machining responses is evaluated using an MQL method instead of MQL under suitable cutting parameters provides an improvement of about 54% and 28% in the cutting force and the cutting temperature. Here, experimental results for the material removal rate and surface roughness are given in figure. Increasing the cutting speed and feed at constant cutting depth caused an increase in material removal rate. If the surface roughness is evaluated, increasing the feed value increases the surface roughness, while increasing the cutting speed decreases the surface roughness. When the effect of cutting environment on the machining responses is evaluated using the NMQL method instead of MQL method under suitable cutting parameters provides an improvement of about 72% in surface roughness. Here, the ranking of the results according to the COCOSO method is given in table. When the resultant force, cutting temperature, surface roughness, and material removal rate results are evaluated together, the best cutting parameters to meet all four conditions are the NMQL cutting environment and 1060 meter per minute cutting speed and 0.08 millimeter per revolution feed value. The conclusions drawn from the study are given below. Resultant force, cutting temperature, and surface roughness are all improved by 54%, 28%, and 72% respectively when applying an MQL method rather than MQL cutting method. Vegetable-based cutting fluid containing molybdenum disulfide nanoparticles have a great deal of the promise to improve the effectiveness of the machining operations. The optimum cutting parameters are determined using the COCOSO method as 1060 meter per minute cutting speed and 0.08 millimeter per feed value, and the best cutting environment is an MQL method. Thank you for your attention. If you have any questions, I can answer them.
Dear participants of the InterPartner-2024 conference, 6th Grabchenko's International Conference on Advanced Manufacturing Processes, we bring to your attention a report on the topic Modeling and Optimization of the Process of Drilling Holes in Carbon Fiber Reinforced Polymer Parts. As introduction, composite materials in future CM are widely used in various industries. This is due to a high strength of these materials, stiffness, corrosion resistance, low coefficient of thermal expansion, electrically insulating properties, and anisotropy of properties, which allows you to control the properties of the final product. Carbon plastics, i.e. composite materials with carbon fibers, and a flexible epoxy resin matrix have become especially popular. Carbon fiber reinforced composite material is a leader in aerospace, defense, and automotive technology due to its unique physical and mechanical properties. For example, the amount of composite materials used in the Boeing 787 aircraft is estimated to be more than 50 of the total weight of the aircraft. Composite materials are made by combining two or more materials to obtain a unique combination of their properties. The general structure of the composite materials is presented in figure. The mechanical processing of the composite materials is adversely affected by the heterogeneous structure of composite material, including the anisotropic, heterogeneous, and highly abrasive characteristics. The quality of machined surface is the most important indicator when evaluating the efficiency of drilling, because it affects the service life of composite parts after assembly. During the drilling process, various defects can be formed, such as delamination, damage to the surface layer, increased roughness and of the machined surface, dimensional error and deviation from roundness. The slide presents the main parameters of the quality of processing holes in composite materials: delamination, damage of surface layer, roughness, dimensional error, and roundness errors. The roughness of the whole surface is one of the main characteristics in the process of composite materials drilling, which is used to analyze the quality of the machined surface by studying the micro uniformities of the surface of the part. A quality parameter similar to roughness is fluffness, that is, the appearance of uncut fibers of fibrous filter above the surface layer. Delamination is the most common defect during drilling. This quality parameter is divided into delamination of the entrance of the cutting tool into the materials and delamination at the exit from it. The main characteristic of the delamination parameters when drilling composite materials is the delamination coefficient, which is determined by the following formula, where Dmax, the maximum diameter of the hole with a damaged area, and D, nominal diameter of the hole. To assess the damage, an approach is used that takes into account the filling area of the maximum diameter of the damaged zone, the delamination structure. Structure of delamination. A is a small cracks. B, a uniform area of damage. The first part of the formula takes into account the size of the crack, which is the delamination coefficient, and the second part takes into account the filling area of the maximum diameter of the damaged zone, where AXP is delamination damage area and A nom, nominal area of the hole. The purpose of the work is to improve the efficiency of drilling holes in carbon fiber parts by means of mathematical modeling and optimization. To achieve the set goal, the following tasks were complete. First, analysis of the feature of the technological processes for processing parts for composite materials and methods of increasing the efficiency. Second, experimental studies of the drilling process of holing carbon fiber parts were carried out in order to obtain mathematical dependencies of the quality surface parameters of the treated holes on the cutting condition and modes. Third, a mathematical model of the drilling process of carbon fiber parts according to the criterion of maximum productivity was developed. Fourth, the problem of determining the optimal modes of drilling holes in carbon fiber parts has been solved. Fifth, computer testing of the functioning of the automated control system for the drilling of carbon fiber parts was carried out, and practical recommendations for the introduction of the system into production were provided. Lamination, roughness of the hole and axial force were chosen as the determining parameters when creating a mathematical model of the whole process and carbon fiber parts. The scheme of relationship of quality parameters when drilling carbon fiber is shown in Figure 5. The fracture mechanics approach was used to analyze the delamination. The critical axial force is presented on Figure 6. The axis of which leads to delamination of the whole surface. This parameter relates the delamination to the properties of the composite material according to the following formula, where GIC interlayer fracture toughness, A1 modulus of elasticity, H the thickness of the uncut layer of the workpiece, and Poisson coefficient. At the same time, the actual value of the critical axial force is less than calculated value by 20 or 40 due to the anisotropy of the composite material. The study of the drilling process of holes with the measurements of the axial force and determination of its values was carried out using an experimental setup, the scheme of which is presented in Figure 7. When conducted experimental studies, carbon fiber and carbon fiber content of 50% with an orientation of 0/90 was used as a processing material. The matrix material was epoxy resin Li 564. The study of the influence of processing conditions and modes feed, number of spindle revolution, and the angle of the top of the drill. On the quality parameters of carbon fiber drilling, the coefficient of delamination and the roughness of the treated surface, and the axial cutting force was carried out. As a result of processing, the results of experimental studies by method of multidimensional statistical analysis, mathematical models of actual cutting force from modes and conditions of drilling were obtained. According to the results of the experimental studies presented in Figure 9, it can be concluded that the value of the axial force and the delamination coefficient can be minimized at high spindle speed and decrease in the feed values. An analytical mathematical model of the delamination coefficient from the axial cutting force and the character of the depends of chi width on the geometric parameters of cutting tools are given. An analytical mathematical model of the roughness of the axial cutting force and the nature of the depends on the geometrical parameters of the cutting tool RA are presents. In the presence of adequate mathematical models of the process parameters of drilling holes in carbon fiber parts, it is possible to determine the influence of cutting modes and conditions on the stability of the cutting process, and to establish the optimal values of the modes that provide the necessary dynamic properties. Optimizing the conditions and regimes in composite material processing involves solving various technological, structural, economic, and organization tasks. When solving the task of finding the optimal modes of processing carbon fiber parts, the maximum productivity N of the process was chosen as a criterion. The value of the critical axial force is calculated based on the properties of the processed material. Then the mathematical model of the drilling process of holes in carbon fiber parts according to the creation of maximum productivity millimeters per minute will have the following form. Therefore, the problem arises of solving one criteria optimization problem of non-linear programming, which is built on the material removal rate model. The optimal modes of drilling with a tool for angles at the top of the drill, which is 60, 100 and 140 degrees, was studied. Formation of the region of admissible solution for different values of the geometric parameters of the cutting tool, drill, angle at the top. Using the graphic method, the limit values of the quality parameters of the obtained holes for different values of the angle of the top of the drill were obtained, which are presented in figure 15, A, B, and C. And conclusion. According to the analysis results of the process of machining parts from composite materials, the main directions for improving their efficiency have been established. It was determined that in order to increase the efficiency of the process of machining parts from composite materials with the provision of the necessary quality parameters, it is necessary to solve the problem of its optimization. In order to build a mathematical model of the parts machining process, it is necessary to obtain mathematical models of quality parameters by conducting relevant experimental studies. Fourth, the researched mathematical model of the optimization of the cutting modes of the drilling process of holes in parts made from polymer composite materials ensures obtaining the specified parameters of the quality of the obtained surfaces with the highest productivity. Fifth, it was established that the creation parameter of the quality of the drilling process of holes in parts made from polymer composite materials as the delamination factor and roughness of the treated surface, which can be determined by the value of the thrust force. 6. As a result of experimental studies, mathematical dependencies of the thrust force, delamination factor, and roughness of the treated surface on cutting modes and conditions were obtained, which allow to form a mathematical model of the process of drilling holes in carbon fiber reinforced polymer. 7th, the optimal drilling modes were obtained by solving a multidimensional problem of nonlinear programming, which ensures the maximum productivity of the process of machining holes with laminations on quality parameters. Thank you for your attention.
Good afternoon, dear General Chair of the conference, members of the steering committee, members of program committee, colleagues scientists. We are pleased to present you a report on the topic a method for determining the forces and coefficient of friction on the back surface of cutting tools and their dependence on processing conditions. Despite the fact the temperature and average stresses on the front surface of the cutting tool are much greater than their counterparts on the back surface, contact process on the latter play a significant role as they determine the intensity of cutting tool wear and its performance. Due to the small size of the contact area on the back surface of the cutting tool, especially at the beginning of cutting, significantly complicates the study of the process characteristics. Due to the low sensitivity of the method, experimental studies were used only for significant size of artificially created contact areas under cutting conditions that do not always correspond to real ones. Currently, the most effective are attempts to combine empirical and modeling research methods. At the same time, the influence of the change in the shape of the contact chamfer during the wear of the contact surface was not taken into account. All these reasons make it difficult to analyze the influence of the factors of the cutting process on the intensity of wear of the back surface of the cutting tool and the choice of optimal processing conditions. Therefore, an actual task is to create an express method for determining the actual cutting forces and friction parameters on the back surface of the cutting tool. To solve this problem, we proposed the method which consists in determining the contact forces on the front surface of the cutting tool at the moment when the chip climb on the front surface of the cutting tool stops. It was suggested that at a certain point in time during the last rotation of the workpiece, when the mechanical feed is turned off, a situation occurs when, due to the small thickness of the cut layer, the formation of chips becomes impossible. So, at this moment, the forces on the front surface of the cutting tool will disappear and the dynamometer will actually record the forces acting exclusively on the rear surface. The ratio of these forces will give the average coefficient of friction on the back surface of the cutting tool. Fixation of this moment is possible only when measure cutting force with a special high-speed computerized device, which was developed at the Khmelnytsky National University. The installation is mounted on a machine with thyristor regulation, which allows you to set any spindle rotation frequency in the wide range. In our case, a UDM 600 model dynamometer is installed on the machine, which allows measuring all components of cutting forces and torque. Another channel is connected to the feed control unit and records the moment it is turned on and off. Two channels are used to control temperature, processes in the cutting zone, and allow connecting both natural and mixed thermocouples. Main technical characteristic you can see on the slide. At the final stage of the last revolution, there is some stabilization on the force, which is displayed on the graph in the form of a short horizontal section, followed by a decrease in force to zero. It was assumed that the horizontal section on the graph corresponds to the moment when the chip stops, and the forces fixed at this moment determine the forces on the back surface of the cutting tool. To check the validity of the proposed method, a series of experiments was conducted to determine the cutting forces on the rear surface of the cutting tool by the classical method of extrapolation to zero slice thickness. A comparison of the obtained results is given in Table 1. Some excess of the values obtained by the method can be explained by the fact that in a classical experiment, one should extrapolate not to zero thickness, but to some value commensurate with the radius of rounding of the cutting edge, when in reality the chip growth process stops. As can be seen on the slide, almost all the studied materials are characterized by a similar extreme dependencies. At the beginning, with the width of the wear chamfer from 0 to 0.12 millimeters, there is an increased coefficient of friction to the values from 1.1 to 1.5. In our opinion, the main influence of the behavior of the curves in the range is played by the adhesive properties of the contact surface of the cutting tool, since they affect the entire complex of phenomena that occur both on the front surface of the cutting tool and on the back surface of the cutting tool. The adhesive properties of the contact can be changed by applying wear-resistant coating. As can be seen from slide, the coating practically eliminates the extremum of the dependence coefficient of friction from chamfer wear. Despite the fact that a zero chamfer that wear coefficient of friction is practically the same in both cutting tools. It was also established that in addition to the adhesive properties of the contact, the friction conditions are influenced by the lubricating and cooling properties of the LCF supplied to the cutting zone. For a shaped tool, the LCF penetrating on the front surface of the cutting tool and the back surface of the cutting tool reduce the force of friction, the temperature, and the height of the inhibited layer on the front surface of the cutting tool. As can be seen from all the above, the proposed method is a fairly informative and quick tool for determining the influence of processing conditions, adhesive properties of coating, lubrication, contact pair of tool workpiece on the coefficient of friction, average normal and tangential stresses on the back surface. Since most tools have a predominant or significant wear on the rear surface, this information in the future can serve as a basis for prediction the intensity of tool wear and the impact of processing conditions on it. In further research, we plan to use the proposed method to evaluate the effectiveness of various types of coatings on the working surface of cutting tools, as well as the influence of various types of lubricants and coolants on processes in the cutting zone. In conclusion, we would like to express our appreciation and gratitude to all colleagues present at the conference for their interest, to the administration of Khmelnytsky National University for assistance in scientific work, to the Armed Force of Ukraine for the opportunity to work safety.
Dear colleagues, we have had 6 reports. All of them were interesting. Let's discuss the results of these reports. as for first presentation, I remember the topic of this presentation is modeling the dynamics of centerless mortise grinding on rigid supports by Vasil Charlie and others. Have you any questions to this report? There are no questions. No. In the chat, online. No questions. I have a question. The topic includes the term mortise grinding. Why mortise? Maybe lunge grinding. How do you think? Vasily Charlie.
Hello everyone. Actually, we use this term because we cut with force indirect to the ring. How to explain actually? Because what you propose, it's more about when we grind surface which are not round. More easier, but for rings, this kind of grinding is more better.
Mortise better than than lunge. Yes.
Yep. Yes.
Okay. There is no question. Okay. As for second presentation, I remember the topic of this presentation. Increasing the continuous operation time of the diamond cutting disc when using various cooling media. It was Alexei Knush. Have you any questions to Alexei?
This presentation is she is in the chat, so you can ask her.
Татьяна Чумаченко. Татьяна Чумаченко, do you hear me?
Yes, Anatoly, Vasily Petrovich.
Vasily, да. No, I don't know. Is there questions to Chumachenko?
No questions.
Oh no. Oh no.
I don't see in the chat any.
In the chat, there is no question. Online, there is no question. Yes. This, I remember this report was about thermal sensor, about equations to calculate temperatures. I was in the hall and I saw one. This is my question to Tatiana. It was one-dimensional equation to calculate temperature. One-dimensional equation. Maybe two-dimensional, maybe three-dimensional. Your presentation is one-dimensional. Why one-dimensional? Not two, not three. Do you hear me? One-dimensional equation to calculate temperature. Not two-dimensional, not three-dimensional, but one-dimensional. What is the error of this calculation? Error in percent. In percent.
Because this dimensional circle cutting using a Rank-Hilsch type and cooling the inhibit disk by cooling medium invitation.
What is the error? Error. Тобто, there is actual temperature and calculated temperature. What is the difference between calculated temperature and actual measured by your thermal sensor? Calculation, difference between theory and practice. Difference in percent.
Because
10, 20,
12%.
12, okay, about 12. About 12, yes?
Yes.
Okay. Now, as for presentation number 3, I remember the topic of this presentation. Development of simulator program for studying the effect of cutting modes on cutting temperature. It was Vladimir Gugnin, Людмила, and so on.
Volodymyr Goloborochka is now in the...
Vladimir Goloborochka. Vladimir Goloborochka. Have you question to Vladimir Goloborochka?
In the chat, no questions.
In the chat, no questions. In the chat, no questions. Так. Online.
No questions.
No questions. So I have a question to you about, you said about automating the processing of measurement, the automated process of measurement temperature in cutting. Yes? Automating processing of measurement automation. Вот. We can see the so-called empirical formulas, but not theoretical. Have you theoretical formula to calculate the temperature? Do you understand me? Theoretical, not empirical, but theoretical formula. Have you? Or no?
Vladimir is in chat, is in the list, but I think isn't untitled. Maybe we can go to the next presentation. And
Next.
In the end, we can ask again.
Okay.
Maybe he has some technical issues.
No. Let's next presentation number 4. Number 4 of 6. 4 of 6. I remember the topic of this presentation. COCOSO method-based evaluation of cutting parameters in tuning of AISI 1040 steel under plane and nanomolybdenous 2 reinforced cutting fluid assisted MQL methods. Are the questions?
In the chat, any questions?
In the chat, any questions? Online?
No questions.
Online also no questions. But it was very interesting topic. It's well-known scientific school in Crimea, if I'm not mistaken. So, yes, so well-known scientific school in Crimea. This presentation was about MQL method, about lubricating lubricants for turning the steel. What is the author of this topic, of this presentation? Do you hear me? May I
Yes, sir.
may I ask you for? Yes, do you hear me?
Yes, sir.
Oh, What about lubricants for the turning?
We use the commercial vegetable-based oil, and we added the molybdenum disulfide nanoparticles for nanofluid assisted MQL method for.
Okay, MQL method. This is minimum quantity lubricant. Yes.
Yes, of course.
This is well-known method, effective method. Very good that this is your topic. This is enough. There is no question.
No.
No.
You don't have questions.
Next presentation, number 5. The topic is modeling and optimization of the process of drilling holes in carbon fiber reinforced polymer parts. Modeling and optimization. Alexander Matoshin. Who it was? I forget who it was. Alexander Matoshin, Sergei Vislov, Viktor Antoniuk, and Oksana Voloshka. It was Alexander Matoshin.
Alexander Matoshin was a speaker, but now there are no speakers in the chat.
There are no questions.
There are no speakers.
Speakers. Speaker. There is no speaker.
Yes.
Now the last presentation, number 6. Topic: a method for determining the forces and coefficient of friction on the back surface of cutting tools and their dependence on processes conditions, by Mykola Mazur and Vladimir Milko. It was Vladimir Milko. Yes? Do you hear me, Vladimir Milko?
I think anyone about this presentation in the chat, so we don't have speakers.
There are no questions, and there is no Milko.
Speakers no.
There is no Milko. I should like my best wishes to Mykola Mazur. Mykola Mazur. This is author of this presentation. This is well-known Ukrainian scientist. I should like my best wishes to Mykola Mazur. Thank you. There is no questions. This is the end of our discussion. Yes?
Thank you very much for your chairing this session and nice presentation of speakers and discussion. Professor Larsen, I appreciate your hard work during this session and wish you all the best. Thank you very much.
Okay. My best wishes to all.
Dear participants, for today we are finishing our conference and we are ready to continue tomorrow according to the agenda. There is no changes, so you can join us tomorrow via YouTube or Google Meet if you want to be actively participate in the discussions or asking the questions. Thank you very much and see you tomorrow. Have a safe evening.
Thank you very much.